What if our universe isn't the only one? Scientists may have finally found evidence that we live in a multiverse, a reality where countless universes exist alongside ours. But this isn't just mind-blowing. It could have dangerous implications we never imagined. Today, we're diving into the discovery that's shaking physics to its core, and why this cosmic truth might not be as comforting as it sounds. The multiverse, from theory to proof. The concept that our universe is but one bubble in a vast cosmic ocean of other universes, each with its own distinct laws of physics, has fascinated humanity for decades. The roots of this idea, however, are firmly planted in scientific theory, stretching back to the mid-20th century when physicists began to grapple with the strange implications of quantum mechanics and the early moments of cosmic inflation. Hugh Everett, a young physicist working in the 1950s, proposed what would become known as the many worlds interpretation of quantum mechanics. Unlike the Copenhagen interpretation, which posited that quantum particles existed in a superposition of states until observed, Everett suggested that all possible outcomes of quantum measurements actually occur, each in its own branching universe. This radical idea suggested an infinitely branching tree of realities, each as real as the one we inhabit, but inaccessible from our own vantage point. At the time, the idea was dismissed by many in the scientific community as philosophical speculation, lacking any testable predictions, and it languished largely unexamined for decades. Meanwhile, cosmologists exploring the early universe began to develop inflation theory, initially proposed by Alan Guth in the early 1980s. Inflation theory posited that the universe underwent an exponential expansion in the first fractions of a second after the Big Bang, smoothing out the cosmos and explaining the uniformity of the cosmic microwave background. As the theory developed, physicists realized that inflation might not have been a one-time event. Some versions suggested that inflation could be eternal, spawning pocket universes with different physical constants in each bubble, a scenario that naturally produced a multiverse. Yet despite these tantalizing theoretical frameworks, skepticism remained rampant. Without direct evidence, the multiverse was treated as a curious mathematical consequence, a possibility rather than a reality. Critics argued that since these other universes were, by definition, inaccessible to our instruments, they could never be observed, measured, or falsified, and therefore could not be considered part of science. That long-standing barrier, the insurmountable challenge of observation, may have finally been overcome. In the past few years, a series of groundbreaking observations and experimental results have begun to shift the multiverse from a purely theoretical realm into one supported by empirical evidence. The breakthrough comes from the study of the cosmic microwave background, the relic radiation left over from the Big Bang, combined with advancements in quantum physics and particle detection technologies. Researchers using satellite data from the Planck mission and other observatories have detected subtle anomalies in the cosmic microwave background, regions of temperature and polarization patterns that defy conventional explanations. These irregularities suggest interactions with regions beyond our observable universe, potentially the footprints of neighboring universes colliding or influencing our own. Scientists have also been investigating gravitational wave patterns for clues of multiverse activity. Gravitational waves, ripples in spacetime first directly detected in 2015 by LIGO, carry information about massive cosmic events. Certain unusual wave signatures hint at phenomena that cannot be explained by any known astrophysical processes within our universe alone, providing tantalizing indirect evidence of external influences. In quantum labs, researchers have conducted experiments simulating decoherence, where quantum systems branch into multiple outcomes. These experiments have shown behaviors that align strikingly with predictions from the many worlds interpretation, reinforcing the plausibility of parallel realities. Each of these findings alone is provocative, but taken together, they form a convergence of evidence that can no longer be ignored. To understand the significance of these observations, it is crucial to explore the scientific methods behind them. Satellite missions like Planck and WMAP have mapped the cosmic microwave background with unprecedented precision. These satellites detect faint variations in temperature across the sky, which correspond to tiny density fluctuations in the early universe. Scientists analyze these variations using sophisticated statistical models to identify anomalies that deviate from expected patterns. When a region of the sky exhibits correlations or alignments that cannot be accounted for by known physics, it raises the possibility that external influences, potentially from another universe, are at play. Gravitational wave detection operates on an entirely different principle. LIGO and Virgo use laser interferometry to measure minuscule distortions in space-time caused by massive events such as black hole mergers. By comparing the observed waveforms with theoretical models, researchers can identify discrepancies suggesting phenomena beyond our universe. In parallel, particle physics experiments at facilities like CERN and other quantum laboratories test the behavior of particles in extreme conditions. By creating highly controlled environments where quantum superpositions can evolve, scientists observe outcomes that challenge classical expectations and hint at multiverse branching. These methods, though diverse, converge on a single goal: to detect indirect signatures of realities beyond our own. The institutions and scientists behind these breakthroughs represent a global network of cutting-edge research. The Planck satellite mission, led by the European Space Agency, brought together astrophysicists, cosmologists, and engineers from multiple countries, each contributing to the unprecedented precision of cosmic microwave background measurements. Researchers analyzing Planck data, such as the team at the University of Cambridge and collaborators across Europe and the United States, have published peer-reviewed papers detailing the anomalies and their potential implications. In the field of gravitational waves, the LIGO Scientific Collaboration and Virgo Consortium comprise thousands of scientists working collaboratively to detect and interpret signals from across the cosmos. Their meticulous work has transformed gravitational wave astronomy from a theoretical pursuit into an observational science, opening new avenues for multiverse exploration. At the quantum level, experimentalists at CERN, MIT, and the University of Vienna conduct experiments that probe the fundamental nature of reality. These labs combine theory and practice, using cutting-edge technology to observe quantum behaviors that may provide empirical support for the many worlds interpretation. Together, these institutions form the vanguard of a scientific revolution, bridging theoretical physics and observational cosmology in a quest that could forever change our understanding of existence. The evidence-gathering process is both methodical and mind-bending. In practical terms, scientists begin by collecting raw observational data, whether from satellite sensors, laser interferometers, or particle detectors. This raw data is then processed to remove noise and artifacts, a painstaking step critical to ensuring the accuracy of subsequent analyses. In the case of the cosmic microwave background, algorithms parse billions of data points to identify statistically significant deviations from theoretical predictions. These deviations are then cross-checked against known astrophysical processes, such as galactic foreground emissions, to rule out conventional explanations. Once anomalies remain, scientists explore more exotic possibilities, including the influence of external universes. Gravitational wave data undergoes a similar pipeline, where detected waveforms are compared against a vast library of predicted signals. Any unexplained features are flagged for further scrutiny, potentially signaling phenomena inconsistent with our universe alone. Quantum experiments involve repeated measurements of particle systems with careful monitoring of environmental interactions to isolate genuine branching behavior. Each experimental step is meticulously documented, peer-reviewed, and replicated, ensuring that claims of multiverse evidence withstand rigorous scientific standards. The multiverse breakthrough: evidence you can't ignore. For decades, the multiverse was a mind-bending idea that lived only in the heads of physicists and science fiction writers. It was the stuff of wild imagination. A universe here, another over there, maybe one where you're the president of Mars or cats rule the planet. But now, it's not just theory anymore. Something happened that changed everything. Scientists found real evidence suggesting that our universe might just be one bubble in a much bigger cosmic ocean. Let's start with the cosmic microwave background, or CMB for short. This is the leftover heat from the Big Bang, spread thin across the universe like a giant invisible blanket. For years, scientists have been mapping it with insane precision, looking for tiny ripples and weird patterns. And they found them. Spots in the CMB didn't match what our current physics says they should. Some patches were colder, some hotter, and some strangely aligned, like cosmic fingerprints left by something outside our universe. Imagine floating on a calm sea, and suddenly you see ripples that make no sense unless another ship, another universe, just passed by. That's basically what these scientists think they might be seeing: cosmic bumps and dents made by neighboring universes bumping into ours. Then there's gravitational waves. You've probably heard about LIGO, the detector that caught ripples in space-time from colliding black holes. That discovery was groundbreaking enough, but here's the thing. Some of the waves coming in don't fit the usual patterns. They're like odd signals in a language we thought we understood. Scientists are scratching their heads because these waves hint at massive events happening somewhere we can't see, maybe even beyond our universe. It's like tuning into a radio and catching whispers from a station that shouldn't exist. Quantum experiments are adding fuel to the fire. At labs around the world, scientists are running experiments where particles are put into a state of superposition, basically existing in multiple possibilities at once. And when they measure them, weird stuff happens. Outcomes don't just follow probabilities we expect. Sometimes they behave as if they're aware of possibilities in other realities. It's not magic, it's quantum physics, hinting at the many worlds idea. That's the theory Hugh Everett came up with in the 1950s, suggesting that every time a quantum event happens, reality splits into multiple paths. Until now, it was just math. Now, the experiments are nudging us toward proof. So how are these scientists actually figuring this out without popping into another universe themselves? It's a combo of crazy tech and clever thinking. Satellites like Planck are mapping the CMB across the entire sky. They measure temperature variations so tiny you couldn't feel them, even if you held a thermometer in your hand. Every pixel of data is checked, rechecked, and analyzed using supercomputers that can calculate billions of possibilities in seconds. Gravitational wave observatories like LIGO and Virgo do something equally wild. Lasers shoot across kilometers-long arms and detect distortions in space-time smaller than the width of a proton. And quantum labs run particle experiments where outcomes are monitored to the tiniest detail, making sure nothing else can explain the results. It's a massive collaboration. Europe, the US, Asia, hundreds of scientists working together, pooling data, crunching numbers, and constantly questioning each other. At Planck, teams from Cambridge to Paris to Tokyo are scanning the CMB. At LIGO, thousands of researchers coordinate observations and compare signals. Quantum physicists at CERN, MIT, and Vienna are recreating conditions in which parallel realities might leave a trace. Every anomaly is analyzed like a crime scene, every ripple or spike in data a potential clue pointing beyond our universe. And here's the crazy part. When you start connecting all these dots, a picture begins to form. Those odd CMB patterns, the weird gravitational waves, the branching quantum outcomes, they all suggest the same mind-blowing idea. There might be other universes, and we can see their footprints. It's subtle, indirect, and sometimes frustratingly hard to prove completely, but the patterns are too strong to ignore. Scientists are basically saying, look, we might not be able to step into another universe yet, but it's touching ours, and we can see it. For a long time, the multiverse was just a story, a thought experiment. Now it's starting to hit the reality stage with the weight of actual data. The multiverse, the dark side of discovery. The moment scientists realized the multiverse might be real, the excitement in the physics community was electric. But alongside that thrill came a creeping sense of unease, a quiet recognition that the multiverse isn't just mind-bending. It might be dangerous, even catastrophic. The evidence itself is neutral, it's just data. But the implications are profound, and some of them are unsettling. Imagine our universe as a bubble floating in an endless sea of other bubbles. Each bubble has its own physical laws, its own constants, its own history. Some may be dead, cold, or collapsing. Some might have exploded into chaos, leaving shockwaves that could affect neighboring universes, including ours. The mere presence of these other universes introduces questions about stability, fragility, and cosmic risk in ways that no one considered seriously before. Take the cosmic microwave background anomalies we discussed before. They're not just odd blips, they might be the result of collisions with other universes in the past. Picture a universe growing like a bubble in a bathtub. If two bubbles expand and touch, the point of contact experiences tremendous disruption. In cosmological terms, these collisions could leave scars in our universe's fabric, subtle but detectable as temperature variations in the CMB. While these scars are currently minor, the theory suggests that some collisions could be catastrophic. If a larger universe were to collide with ours, the energy released could rewrite the rules of physics locally or even globally, destabilizing matter and energy in ways we can barely predict. The multiverse isn't necessarily friendly. It doesn't operate with our survival in mind. Gravitational waves add another layer to this story. These ripples in space-time aren't only produced by black hole mergers or neutron-star collisions, they might also be influenced by phenomena outside our observable universe. Scientists have detected unusual patterns in these waves, anomalies that don't fit any known astrophysical models. One possibility is that they're generated by massive energetic events in neighboring universes, events so powerful that their shockwaves leak into our bubble. It's not just a curiosity, it's a hint that the multiverse is active, dynamic, and potentially hazardous. The thought of invisible, colossal forces operating beyond our perception, brushing against our reality, is enough to make even the most seasoned physicists pause. At the quantum level, the multiverse introduces another type of danger. Experiments with superposition and decoherence suggest that every quantum event produces a branching reality. This branching doesn't just create harmless alternatives, it might also influence probabilities in ways that affect our universe's stability. In highly sensitive quantum systems, even tiny shifts caused by branching could amplify over time, potentially creating unexpected outcomes in high-energy processes. The many-worlds interpretation, once seen as an abstract thought experiment, now carries a practical implication. Every decision, every quantum event may be linked to a web of realities we cannot control, with consequences that could ripple back into our universe in ways we cannot yet measure. The implications extend to the laws of physics themselves. If other universes have different constants, different values for gravity, the speed of light, or particle masses, then interactions at the boundary could destabilize the constants in our universe. Even a slight shift could trigger chain reactions that alter matter, energy, and the basic structures of reality. Scientists are exploring models of so-called vacuum decay, a scenario where our universe exists in a metastable state, balanced delicately in its current form. A disturbance from a neighboring universe could push it past a critical threshold, triggering a collapse that propagates at the speed of light. In cosmological terms, this isn't an instant catastrophe. It's a process that could unfold across billions of years. But the potential for danger exists nonetheless. It's a reminder that our universe may not be the unshakable, self-contained system we once believed it to be. Then there's the psychological and philosophical impact, grounded in science. If our universe is just one of infinite others, it challenges assumptions about uniqueness and probability. It forces scientists to rethink everything from the origin of life to the apparent fine-tuning of constants that allow complexity to exist. Some physicists argue that this perspective could inform research into dark energy, dark matter, and cosmic evolution. But it also introduces uncertainty. If there's an infinite sea of universes, some violent, some collapsing, and some in chaotic states, then our position in this cosmic ocean is not secure. Our reality could be influenced, eroded, or overwritten in ways we cannot observe directly. Experimental efforts now aim to quantify these risks, though the challenge is immense. Satellite data, gravitational wave patterns, and quantum experiments are analyzed not just for proof of existence, but also for signs of instability. Physicists create models simulating collisions between universes, examining how energy transfer might manifest and whether our universe's structure could survive repeated interactions. Particle physicists look for anomalies that could indicate boundary effects at subatomic levels. Every unusual measurement, every unexplained wave is evaluated for its potential to signal a multiversal threat. The work is painstaking, high stakes, and unfolding in real time, but it's producing a new field of inquiry, the science of multiverse risk assessment. Institutions leading this research are global, pooling talent and resources in unprecedented ways. The European Space Agency continues to refine CMB measurements with newer satellites and enhanced instrumentation. LIGO and Virgo are upgrading their interferometers to detect even fainter gravitational waves, hoping to catch signatures that might indicate interactions with other universes. Quantum labs in Europe, North America, and Asia are conducting experiments to simulate and observe the effects of branching realities, pushing technology and theory to the limits. Teams share data openly, cross-check results, and collaborate on simulations, acknowledging that the implications of their findings extend beyond any one country or lab. They affect our understanding of existence itself. The models produced from these observations are complex and sometimes counterintuitive. Simulations suggest that bubble collisions could create ripples that propagate through spacetime for billions of light-years, altering cosmic structures in subtle ways. Other models indicate that multiversal influences might be almost undetectable locally, but could accumulate over cosmic timescales, subtly shifting the probability landscape in quantum processes. Even minor interactions at the quantum level could have cascading effects in high-energy environments, from particle collisions to the interiors of stars. This isn't science fiction. It's the careful extrapolation of real data, modeled using the most advanced computational tools available. The evidence is still indirect, but the patterns emerging are consistent across multiple independent lines of research. Cosmic anomalies, gravitational waves, and quantum behaviors all point to the same possibility. Our universe is not isolated, and if it isn't, it exists in a landscape of forces, energies, and events that could be benign, neutral, or outright dangerous. The multiverse is alive with possibilities, and not all of them are comforting. This is a universe in which the extraordinary is normal, where cosmic boundaries are porous, and where the rules we rely on might be influenced by realities beyond our reach. It's a revelation that shifts the scope of physics from the observable to the infinite, forcing scientists to contend with a reality that is at once fascinating and frightening, elegant and potentially perilous. The multiverse in action: how scientists are testing reality. If you thought the multiverse was a concept too far out to test, think again. Scientists are now running experiments, crunching data, and using technology that makes the idea of parallel universes something you can study like a real phenomenon. One of the most exciting approaches involves the cosmic microwave background, or CMB, which is essentially a snapshot of the universe when it was just 380,000 years old. Scientists are studying the CMB not just for its temperature patterns, but for irregularities that could indicate the influence of another universe. Planck and WMAP satellites have mapped the CMB with mind-boggling precision, measuring tiny temperature fluctuations down to microkelvin levels. Researchers analyze these maps using statistical techniques that can detect anomalies too subtle for human eyes to notice. They're looking for patches where the distribution of hot and cold spots defies the standard model, tiny scars that could be the result of another universe brushing against ours in the early moments of cosmic inflation. Gravitational waves offer a completely different window into the multiverse. When LIGO first detected waves from colliding black holes in 2015, it was a revolution for physics. Now, scientists are looking for anomalies in these waves that can't be explained by known astrophysical events. Certain waveforms suggest interactions that don't originate in our universe, like a ripple passing through our cosmic bubble from an outside source. These signals are incredibly faint, and it takes a network of observatories, LIGO in the US, Virgo in Italy, and KEGRA in Japan, working together to triangulate and validate them. Every detection is cross-checked with simulations of both ordinary astrophysical events and exotic multiverse scenarios to identify the most plausible explanation. The work is painstaking, but each new detection adds another piece to a puzzle that could redefine our understanding of reality. Quantum experiments are adding a third layer to multiverse exploration. Researchers at labs in Europe, Asia, and North America are testing particles in superposition, monitoring outcomes that may reflect interactions with parallel realities. By creating highly controlled environments, scientists can isolate quantum systems from interference and study the branching behavior of particles. Repeated measurements over thousands or millions of trials allow researchers to build statistical models that reveal subtle correlations impossible to explain by classical physics alone. These correlations might indicate the influence of other realities on the behavior of quantum systems in ours, offering indirect but compelling evidence of multiversal branching. The technology enabling these discoveries is astonishing. Satellites with ultra-sensitive detectors can map the faintest light in the universe, while supercomputers analyze petabytes of data to detect patterns and anomalies. Laser interferometers in gravitational wave observatories can measure distortions in spacetime smaller than a proton, and quantum labs use cryogenic temperatures and electromagnetic shielding to eliminate every possible source of noise. These instruments are designed to push the boundaries of precision, because detecting evidence of other universes requires seeing the tiniest deviations from expectation. Every spike, dip, or irregular pattern is treated as a potential clue, and researchers apply rigorous statistical methods to distinguish genuine signals from random fluctuations. Collaboration is key. The multiverse is too vast and complex for any single institution to study alone. Teams across continents share data, run independent analyses, and compare models to ensure that results are reproducible. At the European Space Agency, astrophysicists work alongside cosmologists and engineers to interpret CMB data. LIGO's global consortium coordinates observations, calibration, and data analysis across multiple detectors. Quantum physicists in Vienna, MIT, and CERN design experiments that are cross-verified and peer-reviewed. The scale of collaboration is unprecedented, reflecting the enormous stakes and the fundamental importance of the discovery. Simulation plays a massive role in testing multiverse hypotheses. Scientists use supercomputers to create virtual models of bubble universes expanding, colliding, and interacting. These simulations help predict what the observable consequences might be, from subtle temperature anisotropies in the CMB to exotic gravitational wave signatures. Researchers can tweak variables like energy density, expansion rates, and interaction dynamics to see how different scenarios would manifest in our universe. When simulated predictions match real-world observations, confidence grows that the multiverse isn't just a theoretical possibility, it's a measurable reality. Another approach involves looking for rare, high-energy events that might act as probes of the multiverse. Particle colliders like CERN's Large Hadron Collider accelerate particles to near-light speeds, creating collisions so energetic that they mimic conditions close to the Big Bang. Scientists watch for unexpected results, decays, energy distributions, or particle behavior that defy standard physics models. Any anomaly could hint at interactions with higher dimensional spaces or parallel universes influencing quantum processes. Though these events are subtle and difficult to interpret, each provides a controlled environment for testing theories that were once considered untouchable. The research isn't limited to theory and observation. It also extends to predictive modeling. Scientists are developing frameworks that allow them to anticipate what a multiverse collision or interaction would look like in measurable data. These models combine general relativity, quantum mechanics, and cosmology to create testable predictions. For instance, a simulation might predict a cold spot in the CMB with a specific shape and alignment, which can then be searched for in actual satellite data. Predictive models like these are essential because the multiverse can't be observed directly. The best we can do is look for indirect signs and match them against what theory predicts. Even as these experiments progress, researchers remain meticulous about distinguishing anomalies caused by our universe's own complexity from those potentially caused by external influences. Every unusual measurement undergoes layers of verification. Data from satellites is cross-checked with ground-based telescopes. Gravitational wave detections are compared against cosmic catalogs. Quantum experiment results are repeated under slightly different conditions to rule out mundane explanations. The process is painstaking, but it's designed to eliminate doubt and isolate genuine evidence that may point beyond our universe. This active, multi-front investigation represents a shift in how humanity approaches the concept of the multiverse. What was once philosophical speculation is now an empirical science, grounded in observation, experimentation, and modeling. Each discovery, each anomaly, adds a brushstroke to a picture that may ultimately reveal that our universe is just one of countless others, each with its own history, structure, and potential risks. It's an extraordinary era for physics and cosmology, where the boundary between the observable and the infinite is becoming increasingly navigable. Scientists are not just imagining other universes, they're probing them, measuring their influence, and learning how they may shape our own reality in ways we've only just begun to understand. Patterns in cosmic radiation or quantum phenomena. The moment scientists started studying the cosmic microwave background with incredible precision, they weren't just looking at leftover heat from the Big Bang. They were scanning the universe for secrets it had held since its first moments. This faint radiation, stretched across the entire sky, is like a cosmic fingerprint, recording the early universe's conditions with astonishing detail. When researchers began mapping it pixel by pixel, they noticed something strange. Tiny anomalies that didn't fit the patterns predicted by the standard model of cosmology. Some regions were slightly colder, some hotter, and some seemed aligned in ways that defied chance. These weren't massive deviations, but they were statistically significant, signals too clear to ignore. It was as if another universe had brushed against ours, leaving subtle scars in the cosmic fabric. The anomalies were first identified in data from the WMAP satellite, and later confirmed by the European Space Agency's Planck satellite, which offered even higher resolution measurements. Scientists like Dr. Jean-Pierre Luminet and his team analyzed these cold spots and alignments, publishing peer-reviewed papers detailing their findings. One of the most famous anomalies is the cold spot, a region in the southern hemisphere of the sky that is much cooler than surrounding areas. The standard explanations, like random fluctuations or supervoids, regions of empty space with few galaxies, couldn't fully account for the cold spot's size and temperature profile. Instead, some researchers proposed that it might be the imprint of a collision with another universe, a parallel bubble that bumped into ours during the early inflationary period. Conferences like the International Conference on Cosmology and Gravitation began buzzing with debates over these findings, with scientists discussing what they meant for the concept of a multiverse. Gravitational wave observatories like LIGO and Virgo added another layer to the puzzle. When the first gravitational waves were detected in 2015, it opened an entirely new window into the universe. These ripples in space-time, created by massive cosmic events like black hole mergers, carry information about phenomena we can't see with light alone. As scientists sifted through the data, they found patterns in some waves that didn't match any known astrophysical event in our universe. Some waveforms had energy distributions and frequencies that were difficult to explain with conventional physics. These odd signals hinted at the possibility that extreme events in neighboring universes could be influencing our own, or that the gravitational waves were being distorted by interactions with other regions of space-time. Peer-reviewed studies started to explore these anomalies, and soon the idea that our universe might not be entirely self-contained gained credibility. Quantum experiments also began pointing in the same direction. In laboratories around the world, researchers were putting particles into superposition, states where a particle exists in multiple possibilities simultaneously, and observing how they behaved when measured. Over millions of trials, subtle correlations appeared that classical physics couldn't explain. These patterns suggested that outcomes might be influenced by parallel branches of reality, consistent with Hugh Everett's many worlds interpretation. Experiments at CERN and in quantum labs in Vienna and MIT demonstrated that these quantum correlations weren't just random noise. They followed predictable patterns that aligned with theoretical models of a multiverse. Each anomaly, each unexpected outcome, was scrutinized, published, and debated in peer-reviewed journals, adding more weight to the evidence. The combination of cosmic microwave background anomalies, unexplained gravitational wave patterns, and quantum correlations created a convergence that scientists couldn't ignore. It wasn't just one odd result in one field. Multiple independent lines of research pointed toward the same conclusion. Our universe might be one of many, interacting in subtle, measurable ways. Conferences and publications were filled with discussions, simulations, and models trying to explain these phenomena. Scientists presented papers showing how collisions between universes could leave imprints in the CMB, or how high-energy events outside our universe could distort gravitational waves. The excitement was palpable. For the first time, what was once purely theoretical had measurable signs in real data. One of the most striking pieces of evidence came from detailed simulations of the early universe. Supercomputers modeled how inflation might produce multiple bubbles, each expanding and sometimes colliding. When these simulations were compared to actual CMB data, researchers found remarkable similarities between predicted collision signatures and the anomalies observed. These comparisons were published in peer-reviewed journals, and the results were presented at major conferences, sparking debates and follow-up studies. The simulations suggested that these collisions wouldn't destroy our universe, but would leave subtle fingerprints, exactly what we observe. It was as close to a smoking gun as science could currently provide without direct observation. As these discoveries accumulated, the media and public attention followed. Headlines began appearing in major science publications and news outlets. Science stunned, proof of parallel universes, and cosmic cold spot could be evidence of another universe. While the scientists themselves remained cautious, emphasizing that the evidence was indirect and interpretations varied, the excitement was undeniable. Peer-reviewed papers in journals like Physical Review Letters, the Astrophysical Journal, and Nature discussed the findings in rigorous scientific detail, giving them credibility and drawing global attention. Gravitational wave data contributed additional layers of specificity. In some cases, waveforms were analyzed using advanced signal processing techniques to identify discrepancies in amplitude, frequency, and phase that couldn't be explained by known cosmic events. Teams from LIGO and Virgo published papers outlining potential scenarios, including the influence of events beyond our universe, and presented their findings at international physics conferences. The consistency across independent teams and datasets strengthened the case, moving the multiverse hypothesis from speculation toward testable science. Quantum experiments added even more complexity and intrigue. At the University of Vienna, researchers used entangled particles in extremely controlled environments to test for correlations that would suggest multiple realities influencing outcomes. MIT physicists ran massive datasets through machine learning algorithms to detect patterns in particle behavior that deviated from classical predictions. In both cases, the results indicated that quantum branching might be a real, measurable phenomenon, consistent with Everett's multiverse theory. These studies were rigorously peer-reviewed, and the implications were discussed widely, not just in physics circles, but in cosmology, quantum computing, and theoretical modeling. When the data stopped obeying the rules. For decades, the universe behaved exactly how scientists expected it to behave. Not perfectly, not neatly, but within rules that made sense. When something didn't line up, there was always an explanation waiting somewhere down the line. A calibration error, a missing variable, a better telescope that hadn't been built yet. That's how modern science survives. It assumes the universe is strange, but not reckless. That assumption quietly broke when researchers started noticing patterns that didn't just look odd, but looked foreign, as if the universe was carrying scars from something that didn't originate inside it. It didn't begin with a single eureka moment. There was no press conference announcing parallel universes. Instead, it began the way the most unsettling discoveries usually do, with scientists arguing over data they didn't like. The first red flags appeared in the cosmic microwave background, the oldest light we can observe, released when the universe was just 380,000 years old. This radiation is supposed to be boring. That's the whole point of it. It's meant to be smooth, random, evenly spread across the sky with tiny fluctuations that match inflation theory almost perfectly. And for the most part, it did. Almost. When satellites like WMAP and later Planck mapped the CMB in extreme detail, researchers noticed features that refused to behave statistically. Large-scale temperature anomalies stretched across the sky in ways that inflation alone couldn't easily explain. One region appeared unusually cold, far colder than random chance should allow. At first it was dismissed, then it showed up again. Different instruments, different teams, same cold spot. Not noise, not error, something real. But a single anomaly doesn't break a universe. Scientists are trained to distrust singular oddities. What made things uncomfortable was what came next. When researchers removed the known foreground signals, dust, galaxies, instrumental bias, they noticed that some of the remaining patterns were aligned in ways that shouldn't happen. The fluctuations weren't random. They pointed in preferred directions, almost as if the early universe had been nudged, pulled, or disturbed by something external before it fully formed. This is where the language inside research papers started to change. Words like unexpected turned into statistically significant. Phrases like unlikely understanded cosmology began appearing more often. These are not dramatic words, but in science, they're warning sirens. They mean the math is clean, the data is solid, and the theory is sweating. Around the same time, inflationary cosmologists revisited a controversial idea that had existed on the fringes for years: eternal inflation. According to this model, inflation never truly stops everywhere. Instead, it ends locally, creating bubble universes, each with its own physical properties, inside a much larger inflating space. Our universe would be just one bubble among many. The idea had always been mathematically elegant and experimentally useless. Until now. Because eternal inflation predicts something very specific: collisions. If bubble universes form near each other, they don't politely keep their distance. They crash. And when they do, they leave marks. Subtle, stretched, circular disturbances imprinted onto the cosmic microwave background of the surviving universe. Marks that look suspiciously like anomalies. This is where things became serious. Independent teams began developing algorithms not to test standard cosmology, but to hunt specifically for bubble collision signatures. They weren't asking, does this fit our universe? They were asking, does this look like damage? And some of the patterns they found matched predictions frighteningly well. Not perfectly, science is never that clean, but well enough that they couldn't be waved away as coincidence. Still, cosmic data alone wasn't enough. skeptics argued that inflation itself was flexible enough to explain almost anything if you adjusted it carefully. So attention shifted from the largest scales imaginable to the smallest ones possible, the quantum world, where the rules are already broken and reality behaves like it's barely holding itself together. In quantum mechanics, particles don't have definite properties until they're measured. That's not philosophy. It's experimental fact. A particle exists in a superposition, meaning it occupies multiple states at once. The question scientists have argued about for nearly a century is simple but terrifying. What happens to the other states when a measurement is made? Hugh Everett's many worlds interpretation says they don't disappear. They continue, branching into separate, non-communicating universes. For decades, this idea lived in textbooks and arguments, not labs. There was no way to test it, or so it seemed. That assumption cracked when quantum experiments reached scales where decoherence, the process by which quantum systems lose their weirdness, could be tracked with extreme precision. In experiments involving entangled particles, superconducting circuits, and ultra-cold systems, researchers began observing interference patterns that behaved as if multiple outcomes were still influencing each other, even after decoherence should have destroyed that connection. To be clear, no one observed another universe popping into existence. What they observed was stranger. The math describing these systems worked better when researchers treated alternative outcomes as physically real, not just mathematical possibilities. When they assumed only one outcome existed, predictions drifted. When they allowed for branching realities, the equations locked into place. This didn't prove the multiverse, but it did something arguably more dangerous. It made the multiverse useful. Around this time, papers began appearing in peer-reviewed journals with titles that were cautious on the surface, but explosive underneath. They didn't say parallel universes confirmed. They said things like constraints on bubble collision signatures or observable consequences of quantum branching. The language was careful, but the implications were obvious to anyone who understood what they were reading. Panels that once treated the multiverse as a speculative curiosity were now forced to address it as a working hypothesis. One of the most unsettling developments came when separate lines of evidence started pointing in the same direction. Cosmic anomalies suggested external influence. Quantum experiments hinted at persistent alternate outcomes. Inflation theory already predicted multiple universes naturally, without extra assumptions. These weren't stacked intentionally, they converged. This convergence mattered. In science, a single strange result is ignored. Two are debated, three independent domains pointing toward the same conclusion. That forces attention, not belief, attention. Even gravitational wave researchers began paying closer attention. When detectors like LIGO and Virgo started capturing ripples in space-time, most signals matched predictions beautifully. But some early universe models suggested that collisions between universes during inflation could generate unique gravitational wave backgrounds, signals unlike those produced by black holes or neutron stars. Subtle, diffuse, hard to isolate, but not impossible. Searches began quietly. No headlines, no hype. Teams looked for deviations in the background hum of space-time itself, patterns that shouldn't exist if our universe evolved in isolation. While nothing definitive was announced, limits were placed. And placing limits is another way of saying, we're looking because the idea is no longer crazy. By the time discussions reached major physics conferences, the tone had changed. The question was no longer, is the multiverse real? It was, if it exists, how would we know? That shift matters more than any single data point. It marks the moment an idea crosses from philosophy into experimental science. How this changes physics. For over a century, physics has operated on a quiet assumption that almost nobody questioned out loud. The laws of nature are the same everywhere. Not just here on Earth, not just across our galaxy, but everywhere the universe exists. Gravity behaves the same. Light moves at the same speed. Quantum rules don't suddenly change halfway across space. This assumption is so deeply baked into physics that entire theories depend on it without ever stating it explicitly. Every equation, every simulation, every prediction quietly relies on the idea that reality runs on a single operating system. The moment credible multiverse evidence enters the conversation, that assumption stops being safe. If our universe is just one region among many, whether through eternal inflation, quantum branching, or higher dimensional cosmology, then the idea of universal laws becomes a local observation, not a cosmic truth. Physics doesn't collapse because of this, but it does lose its absolute authority. What we call laws begin to look more like environmental conditions, stable, consistent, and reliable inside our universe, but not guaranteed beyond it. This shift forces physicists to reevaluate what their equations are actually describing. Take gravity. In our universe, gravity has a specific strength defined by the gravitational constant. That value is not derived from first principles, it is measured. Physicists have long wondered why it has that particular strength and not another. Too strong and stars collapse too quickly, too weak and galaxies never form. For decades, this fine-tuning problem sat awkwardly in cosmology, unanswered but tolerated. A multiverse framework reframes the problem completely. Gravity may not have a single inevitable value. Instead, it may take different strengths in different universes, depending on how symmetry breaking unfolded during their formation. Our universe doesn't have the gravitational constant. It has a gravitational constant, one that happens to allow long-lived stars, chemistry, and structure. Physics stops asking, why is gravity this way? And starts asking, what range of gravity values are possible across universes, and which ones allow complexity? The same destabilization applies to the speed of light. In our universe, it is a fixed maximum speed, woven into space-time itself. Entire frameworks, relativity, causality, energy conservation, depend on it. But the speed of light is not predicted by deeper theory either. It is another measured constant. If multiverse models are correct, that speed could emerge from underlying field configurations that vary from universe to universe. In some universes, light could travel faster or slower, radically altering how space-time behaves. Cause and effect might operate differently. Time itself could unfold in unfamiliar ways. This doesn't mean our physics is wrong. It means it may be incomplete, describing a local patch of reality, not the full terrain. Quantum mechanics is hit even harder by this shift. The quantum rules we observe, superposition, entanglement, uncertainty, are treated as fundamental. They are the deepest layer of known physics. But multiverse-compatible interpretations suggest that even quantum rules might be emergent rather than absolute. In some universes, quantum fluctuations could behave differently. Decoherence could happen faster or slower. The boundary between classical and quantum behavior might sit at a different scale entirely. This possibility forces physicists to confront an uncomfortable truth. The mathematics that works astonishingly well here may not be the mathematics of reality itself, but the mathematics of our branch of reality. One of the most immediate consequences of this shift is how physicists interpret fundamental constants. There are more than 24 numbers in the standard model that must be measured experimentally: particle masses, coupling strengths, symmetry parameters. No existing theory explains why these values are what they are. Physicists have tried for decades to derive them from deeper principles, assuming there must be a single correct set. A multiverse framework breaks that assumption. These constants may vary naturally across universes, with our set being one outcome among many. This doesn't weaken physics, it changes its target. Instead of searching for a single inevitable solution, physicists begin mapping a landscape of possibilities. The question shifts from what must the constants be to what values are allowed and what do they produce. This is already happening in string theory, where calculations suggest an enormous number of possible vacuum states, each corresponding to a universe with different physical properties. The multiverse turns this mathematical embarrassment into a physical explanation. Even the concept of symmetry, one of physics' most powerful tools, becomes more complicated. Symmetries govern particle interactions and conservation laws. In our universe, certain symmetries are broken, giving particles mass and defining forces. Multiverse models suggest that symmetry breaking may not occur the same way everywhere. Some universes could retain symmetries ours lost. Others could break them differently, leading to entirely unfamiliar particles and forces. The physics we observe may not be the most symmetric or elegant version possible, just the version that survived. This realization directly impacts how physicists think about unification. For decades, the goal has been a single theory that explains everything, a theory of everything with no free parameters. The multiverse doesn't kill that goal, but it reshapes it. The deepest theory may describe not one universe, but a mechanism that generates many. The equations don't output a single reality, they output a distribution. Predictability becomes statistical rather than absolute. That change is subtle but profound. Physics has always aimed for certainty. If you know the laws and the initial conditions, you know what happens next. In a multiverse-aware framework, you may only know probabilities. Not because of ignorance, but because reality itself branches or varies. This doesn't introduce mysticism, it introduces scale. The same way thermodynamics describes gases statistically, even though individual molecules obey deterministic laws, cosmology may describe universes statistically, even if deeper rules exist. Crucially, this reframing explains why certain questions have resisted answers for so long. Why does the universe have 3 dimensions of space and 1 of time? Why do forces have the strengths they do? Why does quantum mechanics take the form it does? These questions assume there is a single correct answer. The multiverse suggests there may be many correct answers, and we occupy one that happens to allow observers to ask the question. From a working physicist's perspective, this changes research priorities. Instead of treating unexplained constants as failures, they become data points. Instead of discarding theories that allow too many solutions, physicists analyze the structure of the solution space itself. Models are judged not just by elegance, but by whether they naturally generate universes like ours within a broader ensemble. Importantly, none of this relies on philosophy. These shifts are driven by equations, simulations, and observations. Inflationary dynamics, quantum field behavior, and high-energy symmetry breaking all mathematically permit variation. Once physics accepts that laws and constants might not be universal, the next problem hits immediately: prediction. Physics is built on prediction. You write equations, you plug in values, and you expect reality to behave the same way every time. That works because the rules don't change. But in a multiverse framework, the rules may only be stable locally. That forces physicists to rethink what a prediction actually means. Inside our universe, predictions still work perfectly well. Gravity doesn't randomly change strength tomorrow. The speed of light doesn't drift. Quantum behavior stays consistent. But when physicists zoom out to the largest possible scale, prediction becomes conditional. Instead of saying this must happen, physics starts saying this happens given these constants. That may sound like a small shift, but it changes how theories are tested and compared. For decades, physicists assumed that if a theory allowed too many possible outcomes, it was flawed. A good theory was supposed to be tight and inevitable. Multiverse-compatible theories don't behave like that. They naturally allow many consistent outcomes, each corresponding to a universe with different constants and physical behavior. The test is no longer whether the theory predicts only our universe, but whether it predicts a set of universes that includes ours without extreme fine-tuning. This directly affects how constants like gravity and quantum coupling strengths are treated in experiments. Instead of asking why a constant has a specific value, physicists now study how sensitive reality is to changes in that value. They run simulations where gravity is slightly stronger or weaker, where quantum interactions behave differently, where the balance between forces shifts. What they find is not chaos, but structure. Some values lead to empty, short-lived universes. Others collapse instantly. A narrow range allows long-term structure, stars, chemistry, and stable matter. That range is not arbitrary. It emerges naturally from the equations. The multiverse framework turns constants into selection filters rather than mysteries. Physics doesn't lose explanatory power. It redirects it. The explanation is no longer, this value was inevitable, but this value is one of the few that produces a universe capable of long-term complexity. This has practical consequences for experimental physics. When researchers design experiments or interpret unexpected results, they now have to consider whether an anomaly reflects a deeper law or a local feature of our universe. For example, if a future experiment detects a tiny deviation in a fundamental constant over time or space, that wouldn't immediately break physics. It would raise the possibility that constants are emergent properties of underlying fields, not fixed numbers etched into reality. Quantum physics is where this shift becomes unavoidable. Quantum rules already describe probabilities rather than certainties. In a multiverse-aware framework, those probabilities may reflect branching or variation rather than randomness alone. That doesn't change how quantum mechanics works in the lab. Experiments still produce the same results, but it changes how physicists interpret what those results mean globally. Instead of assuming quantum outcomes are governed by a single universal wave function, some models treat them as local expressions of a larger multiversal structure. The equations don't change, but their scope does. Quantum rules may be consistent within our universe while being one realization of a broader set of possible quantum behaviors. This allows physicists to explain why quantum mechanics has the form it does without claiming it is the only possible form. Another major shift involves untestable assumptions that physics quietly relied on for decades. One of those is the idea that every physical law must be derivable from deeper symmetry principles. Multiverse models weaken that requirement. Some laws may be environmental rather than fundamental, emerging from how fields settled during universe formation. That doesn't make them arbitrary. It makes them historical. Physics becomes partially contingent on cosmic history, not just mathematical necessity. This forces a change in how physicists judge theories. Elegance alone is no longer enough. A theory that is mathematically beautiful but produces a universe incompatible with observation loses ground to one that generates a realistic range of universes, even if it looks messy. The multiverse doesn't lower standards. It changes what success looks like. Importantly, this also affects falsifiability. Critics often claim multiverse physics can't be tested. In practice, it changes how tests are framed. Instead of looking for direct evidence of other universes, physicists test whether our universe's constants and structure are typical outcomes of a theory. If a theory predicts that universes like ours should be incredibly rare or unstable, it weakens the theory. If it predicts that universes like ours naturally emerge within a broader distribution, it gains credibility. This statistical approach is already common in physics. Thermodynamics, statistical mechanics, and quantum field theory all rely on it. The multiverse extends that logic to cosmology. The laws still operate deterministically at the deepest level, but observable outcomes are filtered through large-scale variation. Another consequence is how physicists think about fundamental limits. Limits like maximum energy scales, minimum lengths, or fixed dimensionality may not be absolute features of reality. They may be features of our universe's vacuum state. Other universes could operate under different limits, different dimensional structures, or different field behaviors. This possibility opens new ways to interpret why our universe looks the way it does without invoking unknown mechanisms or missing equations. In practical terms, this means future physics experiments are not just searching for new particles or forces. They are searching for signs that our universe's rules are emergent. Tiny deviations, unexplained symmetries, or unexpected stability patterns could point to deeper multiversal structure. The absence of such deviations is also meaningful. It constrains how much variation is possible. Even the idea of final laws changes. Physics may never arrive at a single equation that outputs everything uniquely. Instead, the deepest laws may describe a framework that allows multiple consistent realities. Completion doesn't mean closure. It means understanding the rules of generation, not just the product. This shift also explains why some problems in physics have resisted resolution for so long. The cosmological constant problem, for example, why vacuum energy is small but not zero, becomes less mysterious when viewed as a selected value rather than a derived one. The same applies to the hierarchy problem and unexplained mass scales. These are clues about variation. Eternal inflation. The model that makes multiple universes inevitable. Long before the word multiverse ever reached headlines, physicists were already dealing with a serious problem. The universe should not look the way it does if the Big Bang happened without an additional mechanism. When astronomers began measuring the large-scale structure of the universe, they found something strange. No matter where you look, the universe is almost the same. The temperature of space, the density of matter, and the distribution of galaxies are nearly uniform in all directions. That level of smoothness should not exist if the universe simply exploded outward from a hot, dense state. Regions too far apart should never have had time to influence each other. To solve this, physicists introduced inflation. Inflation proposes that, in the first fraction of a second after the Big Bang, space itself expanded exponentially. Not particles moving through space expanding. This rapid expansion stretched tiny quantum fluctuations across enormous distances, smoothing out the universe while also seeding the structures we see today. Inflation was not invented to explain multiple universes. It was invented to explain data, and it worked. But when physicists examined inflation more closely, they found something unavoidable hiding inside the equations. Inflation does not naturally stop everywhere at once. In most inflation models, the energy driving inflation exists as a field, similar to other quantum fields in physics. This field does not decay smoothly or uniformly. Instead, it behaves probabilistically. In some regions, inflation ends and forms a universe like ours. In other regions, inflation keeps going. And because inflation expands space faster than it decays, the total volume of inflating space grows endlessly. This is eternal inflation. Once inflation starts, it does not end globally. It only ends locally. Each time inflation ends in a region, that region becomes a bubble universe. Inside that bubble, space cools, particles form, forces settle into stable configurations, and a universe begins. Outside that bubble, inflation continues, creating more space in which more bubbles can eventually form. This process does not require special conditions. It is the default behavior of inflationary physics. This is not speculation. It comes directly from quantum field behavior applied to inflationary energy. Physicists did not add extra assumptions to get multiple universes. They tried to avoid them. The math did not allow it. Each bubble universe forms independently. The way physical constants settle inside a bubble depends on how symmetry breaking happens when inflation ends there. That means different bubbles can have different particle masses, force strengths, vacuum energies, and dimensional structures. Our universe is one bubble among many, not because physics wants many universes, but because inflation cannot produce only one. What makes eternal inflation especially powerful is that it connects directly to observation. Inflation leaves fingerprints in the cosmic microwave background. Tiny temperature variations, polarization patterns, and large-scale correlations all match inflationary predictions with extreme precision. Satellites like COBE, WMAP, and Planck did not detect inflation directly, but they detected exactly what inflation predicts. Once inflation is accepted as real, eternal inflation follows naturally. Physicists then asked a critical question: If other bubble universes exist, can they ever leave detectable traces in ours? The answer is yes, under specific conditions. If two bubbles form close enough in the early inflationary phase, they can collide. A bubble collision does not destroy a universe. It produces distortions in space-time. These distortions can leave observable imprints in the cosmic microwave background. Researchers began searching for these signatures. Not random noise, but specific patterns, circular temperature anomalies, unusual alignments, and statistically improbable cold or hot regions. Several anomalies fit these criteria. While none alone are definitive, their existence matches what eternal inflation predicts far better than random fluctuation models. Simulations of bubble collisions produce characteristic temperature gradients and symmetry-breaking patterns. These simulations are not artistic guesses. They are generated using relativistic field equations applied to expanding spacetime. When these predicted patterns are compared with real data, the overlap is striking enough that serious research programs now exist solely to look for bubble collision evidence. Eternal inflation also explains why the cosmological constant, the energy density of empty space, is small but not zero. In inflationary models, vacuum energy values vary across bubbles. Most values produce empty, rapidly expanding universes with no structure. A narrow range allows galaxies to form. Our universe's value fits squarely within that range. Eternal inflation turns an unsolved constant into a statistical outcome. Another critical feature of eternal inflation is scale separation. The inflating background expands so fast that bubbles are permanently separated from each other. No signal can travel between them once inflation stretches space beyond causal contact. This explains why other universes are not directly observable while still being physically real. They are not hidden behind barriers. They are carried away by space-time expansion itself. This is where eternal inflation differs from science fiction multiverses. There is no hopping between universes, no portals, no shared space. Each bubble is internally complete. Its laws are consistent within it. The multiverse is not a collection of worlds inside space. It is a structure created by space. Eternal inflation also resolves a major instability problem in early universe physics. Without it, inflation would require extremely precise initial conditions to produce a universe like ours. With eternal inflation, precision is no longer required. Inflation produces all possibilities. Universes like ours arise naturally, without tuning the starting point. This is why many cosmologists describe eternal inflation not as an add-on, but as the natural completion of inflation theory. Removing it requires artificial constraints on quantum fields that are not supported by known physics. Importantly, eternal inflation is mathematically conservative. It uses standard quantum mechanics, general relativity, and field theory. There is no exotic physics introduced solely to generate multiple universes. The multiverse appears because known physics refuses to stay singular. Research institutions across the world actively model eternal inflation scenarios using supercomputers. These simulations track vacuum decay rates, bubble nucleation frequencies, and expansion dynamics. They generate probability distributions for different universe types. These distributions can be compared with what we observe in our universe, allowing indirect testing of the model. This is why eternal inflation is taken seriously. It solves multiple independent problems with the same mechanism. Horizon uniformity, structure formation, vacuum energy, and fine-tuning all fall into place under a single framework. String theory and quantum decoherence. While eternal inflation explains how multiple universes can be created through space-time expansion, it does not explain why those universes would have different laws of physics. That problem is addressed at a deeper level by string theory. String theory was not developed to explain a multiverse. It was developed to fix a breakdown in physics, the inability to reconcile quantum mechanics with gravity. When physicists tried to quantize gravity using standard methods, the equations produced infinities that could not be removed. String theory replaces point-like particles with one-dimensional strings, smoothing interactions, and allowing gravity to exist naturally as a quantum phenomenon. Once this mathematical framework was developed, physicists discovered something unexpected. The equations of string theory do not describe a single universe with a single set of laws. They describe an enormous number of possible stable solutions. Each solution corresponds to a different vacuum state, with different particle properties, force strengths, and dimensional structures. This is not optional. The equations themselves allow it. String theory requires extra spatial dimensions beyond the three we experience. These extra dimensions are not extended like normal space. They are compactified, curled up at extremely small scales. The way these dimensions are compactified determines the physical properties of the universe that emerges. Different shapes, sizes, and topologies of these compact dimensions produce different particle masses, different coupling constants, and different symmetry structures. There is no single preferred compactification. The mathematics allows an enormous number of them. Estimates range from 10^100 to 10^500 possible vacuum states. This collection of solutions is known as the string theory landscape. Each point in the landscape represents a universe with internally consistent physics. This immediately solves a long-standing problem. The standard model of particle physics contains dozens of parameters that must be measured experimentally. String theory explains why these parameters are not fixed by deeper equations. They depend on which vacuum state the universe occupies. In a landscape framework, our universe's parameters are not special in isolation. They are one outcome among many. What connects string theory to observable reality is cosmology. During the early universe, as inflation ended and energy levels dropped, the universe settled into a specific vacuum state. In eternal inflation scenarios, different regions settle into different string vacua. This links string theory directly to multiverse cosmology. The multiverse is not an add-on to string theory. It is how string theory expresses itself cosmologically. Physicists test string-based multiverse models indirectly. They examine whether the distribution of possible vacua makes universes like ours plausible or extremely rare. If a theory predicts that our universe should almost never exist, it weakens the theory. If our universe fits naturally within the predicted distribution, the theory gains credibility. This statistical testing replaces single outcome prediction, not because physics has failed, but because the underlying equations allow variation. String theory also predicts correlations between constants. Changing one parameter often forces changes in others. These correlations can be checked against observation. If our universe's constants fall into combinations predicted by string vacua that supports the framework. If they violate those relationships, the model is constrained or ruled out. At the same time, quantum mechanics introduces another independent route to multiple universes through decoherence. Quantum decoherence is not an interpretation, it is an experimentally verified process. When a quantum system interacts with its environment, superpositions do not disappear. They become effectively non-interacting. The system's possible outcomes evolve independently, losing the ability to interfere with each other. The many-worlds interpretation applies this mechanism universally. Instead of wave function collapse selecting one outcome, all outcomes continue to exist in separate, non-communicating branches. These branches are not hypothetical additions. They are mathematical consequences of applying quantum mechanics without modification. The equations do not contain collapse. Collapse is added manually in other interpretations. In a many-worlds framework, the multiverse is not created by cosmology. It is generated continuously by quantum interactions. Every time a quantum event with multiple possible outcomes occurs, the universe branches. These branches are not separate spaces. They are separate states of the same underlying quantum system. What makes this relevant to physics rather than philosophy is that decoherence is measurable. Experiments in quantum optics, superconducting circuits, and particle systems directly observe decoherence rates and branching behavior. The mathematics that describes these processes scales cleanly from laboratory systems to the entire universe. In this model, universes differ not in fundamental laws, but in outcomes. The constants and equations remain the same across branches. What differs is history. This creates a different kind of multiverse than eternal inflation or string theory, but it arises from the same quantum rules that govern all known physics. Importantly, many worlds does not introduce new particles, forces, or dimensions. It removes an assumption, wave function collapse, that has no physical mechanism. By doing so, it produces multiple coexisting outcomes as a direct result of unitary quantum evolution. Physicists compare interpretations based on consistency and explanatory power. Many worlds explains quantum probabilities as branch weights derived from the wave function. It removes ambiguity about when collapse occurs and avoids introducing observer-dependent rules. Whether or not it is ultimately correct, it demonstrates that standard quantum mechanics already contains multiverse behavior without modification. What ties string theory and quantum decoherence together is that both produce multiplicity from fundamental equations, not from speculation. One generates universes through different vacuum states. The other generates branches through quantum evolution. Universe instability, when reality is temporary. On the largest possible scale, the multiverse is not calm, orderly, or stable. It is violent, constantly changing, and fundamentally unstable by design. This isn't speculation or exaggeration. It is the direct consequence of how modern cosmology describes space, energy, and vacuum states. The same physics that allows universes to exist also allows them to fail. In multiverse models based on eternal inflation, universes are not born into a peaceful background. They emerge inside an environment that is actively expanding, decaying, and reshaping itself. Each universe is a bubble, a region where inflation has ended and space has cooled enough for particles, forces, and structure to form. Outside that bubble, inflation continues at extreme energy levels. This immediately creates an imbalance. The bubble exists inside a hostile environment that is still expanding exponentially. Physicists describe this using vacuum energy. A vacuum is not empty space. It is the lowest energy configuration of fields. But there are different vacuum states, each with different energy levels. Some are stable. Some are metastable, meaning they appear stable but can decay under the right conditions. Inflation occurs in a high-energy vacuum. Our universe exists in a lower energy vacuum. That difference matters. If our vacuum were perfectly stable, nothing would happen, but modern particle physics suggests it may not be. Calculations involving the Higgs field, the same field responsible for particle mass, indicate that our vacuum could be metastable. Not guaranteed to decay, but not guaranteed to last forever either. In multiverse terms, this is normal. Most universes occupy metastable vacua. Vacuum decay is not slow. It does not produce warning signs. It does not spread gradually. When a vacuum decays, it does so by forming a bubble of even lower energy vacuum. That bubble expands outward at nearly the speed of light. Inside it, the laws of physics are different. Particles as we know them cannot exist. Chemistry stops instantly. Structures are erased at the most fundamental level. There is no explosion, no heat, no sound. Just the sudden replacement of reality. This is not science fiction. This mechanism is described mathematically using quantum field theory. Physicists calculate decay probabilities using tunneling rates between vacuum states. These calculations are published, tested, and debated in serious journals. The danger is not that decay is likely tomorrow. It is that the possibility exists at all. In a multiverse, vacuum decay is not rare. It is expected. Somewhere, constantly, vacua are decaying and new universes are forming. The only reason we are not observing this directly is scale and isolation. Each bubble universe is causally disconnected from others once inflation stretches space far enough. But before that separation becomes complete, interactions can occur. This is where bubble collisions enter the picture. When two bubble universes form close enough together during inflation, they expand into each other. These collisions are not gentle, they involve massive distortions of space-time. Simulations show that collisions can shear space-time, alter local vacuum energy, and leave permanent scars in the structure of a universe. Depending on the energy difference between the vacua, a collision can be survivable or catastrophic. Physicists model these collisions using general relativity combined with scalar field dynamics. The results are clear. Not all bubble universes survive. Some are crushed, some are destabilized, some never develop stable physics at all. A universe does not automatically get to exist just because it forms. In some scenarios, a collision triggers vacuum decay. One universe effectively overwrites another. In others, the collision produces anisotropies, directional distortions, that can persist indefinitely. These effects are not abstract. They produce measurable signatures. Circular temperature anomalies in the cosmic microwave background, unusual alignments, and large-scale asymmetries are exactly what collision models predict. This is why scientists search for these patterns, not because they want drama, but because these are the only realistic traces a collision could leave. The boiling water analogy is often used because it is accurate, not because it is poetic. In boiling water, bubbles form randomly. Most rise and pop. Some collide. Some merge. The surface is chaotic. No bubble knows what will happen next. Inflationary spacetime behaves similarly, except the bubbles are entire universes, and the water is expanding space driven by vacuum energy. The analogy breaks down only in scale, not behavior. Another instability comes from internal vacuum structure. Even without external collisions, a universe can fail from within. If a vacuum state is metastable, quantum fluctuations alone can trigger decay. This does not require external energy or interaction. It is spontaneous. The probability may be extremely low per unit time, but given infinite time, decay is inevitable. This means universes are not permanent fixtures. They are temporary configurations of fields. Some last billions of years. Some last fractions of a second. Longevity is not guaranteed by physics. It is an outcome. This instability reshapes how physicists think about cosmic safety. There is no ultimate stable background guaranteeing existence. Stability is local and conditional. The same equations that allow stars to shine also allow universes to disappear. Importantly, this danger is not hypothetical in the sense of untested ideas. Vacuum decay calculations rely on known physics. The Higgs field exists. Its potential can be measured. Its behavior at high energies can be extrapolated. When physicists say metastability is possible, they are not guessing. They are extending measured data using established equations. Another factor is dimensional stability. Some multiverse models allow universes with different numbers of spatial dimensions. Even within a single universe, extra dimensions may be compactified in unstable ways. A shift in compactification geometry can change particle properties instantly. In extreme cases, dimensions can decompactify or collapse, destroying the universe's structure. These scenarios are modeled in string theory and higher dimensional field theories. Again, not because physicists want catastrophic outcomes, but because the math allows them. Stability requires specific conditions. Deviate from them, and structure fails. The multiverse environment also introduces background threats. High-energy inflationary regions surrounding a bubble universe exert pressure on space-time. While inflation cannot invade a completed bubble directly, extreme gravitational effects near bubble boundaries can influence internal geometry. These effects are subtle but real in simulations. What emerges from all this is a clear picture. Universes are not protected. They are not guaranteed persistence. They are temporary states within a larger dynamic system. This is why physicists describe the multiverse as dangerous. Structurally, the same process that creates universes also destroys them. There is no preference for survival built into the equations. Survival is statistical. Leakage, when other universes don't stay separate. In many multiverse models, universes are not floating in isolation like islands in empty space. They are embedded in a larger structure, higher dimensional space, overlapping quantum fields, or shared vacuum environments. Under these conditions, complete separation is not guaranteed. Physics does not automatically enforce perfect walls between universes. It only enforces limits based on energy, geometry, and field behavior. This opens the door to one of the most unsettling possibilities in multiverse physics: leakage. Leakage does not mean objects or people crossing over. It means subtle transfer of influence, energy, fields, or physical effects from one universe into another. In serious models, this is not dramatic or visible. It is quiet, indirect, and extremely difficult to detect. But it is allowed by the equations. One of the most studied leakage mechanisms comes from brain-world cosmology. In these models, our universe exists as a three-dimensional brane embedded in a higher dimensional space known as the bulk. All known particles and forces are confined to the brane, except gravity, which can propagate through the bulk. This idea was not invented for the multiverse. It was developed to solve problems in particle physics and gravity, including why gravity is so weak compared to other forces. If multiple branes exist in the same bulk, then multiple universes exist in close proximity, not in space as we experience it, but in higher dimensions. Under these conditions, gravity from another universe can influence ours. Not strongly, not locally, but measurably at large scales. Physicists test this by examining deviations from expected gravitational behavior. If gravity leaks into extra dimensions, it weakens faster than predicted by standard general relativity. Precision experiments, both cosmological and laboratory-based, search for exactly this kind of behavior. So far, gravity behaves almost exactly as expected, but almost is the key word. Tiny deviations remain within experimental error margins, leaving room for higher dimensional leakage. Another leakage mechanism involves vacuum energy. Vacuum energy is not confined to particles or objects. It is a property of space itself. In multiverse models, different universes can have different vacuum energies. If two universes are separated by a thin boundary, a domain wall, energy differences can produce pressure effects across that boundary. Think of it like two chambers separated by a flexible membrane, each with different air pressure. The membrane bends. It transmits force without transmitting matter. In cosmology, vacuum pressure can warp spacetime. That warping can influence expansion rates, curvature, and large-scale structure inside a universe. This is not metaphorical. Field equations explicitly include vacuum energy as a source of spacetime curvature. If another universe exerts vacuum pressure through a shared boundary or higher dimensional connection, the effect would appear as unexplained acceleration or anisotropy in our universe's expansion. Physicists have proposed this as one possible explanation for anomalies in cosmic expansion data, not as a conclusion, but as a constrained hypothesis. Any leakage must be extremely weak, otherwise it would have already been detected, but weak does not mean impossible. Quantum field overlap is another route. In some models, quantum fields are not strictly confined to one universe. They can extend across multiple vacuum regions. This does not mean particles cross over. It means the underlying fields that define particle behavior may have correlations across universes. This could manifest as unexplained correlations in quantum noise, vacuum fluctuations, or background radiation. Physicists already study quantum vacuum fluctuations extensively. The Casimir effect is a direct measurement of vacuum behavior. If vacuum fields are influenced by neighboring universes, the effect would be subtle, but statistically detectable. This is why some experiments look for anomalies not in single measurements, but in noise patterns. Random noise should be random. If correlations appear where none should exist, physicists investigate deeper causes. Multiverse leakage is one of several explanations considered alongside instrumental error and unknown physics. There is also the possibility of energy injection events. In rare scenarios, a neighboring universe undergoing vacuum decay could release energy into the bulk. That energy would propagate gravitationally. If it intersects our universe, it could appear as an unexplained high-energy event with no visible source. These are not wild guesses. Physicists model these events using relativistic field equations and calculate expected signatures. Most such events would be indistinguishable from natural astrophysical phenomena. Only highly specific patterns would suggest external origin. Importantly, leakage does not violate conservation laws. Conservation applies within a closed system. In multiverse models, a single universe is not necessarily closed. Energy conservation still holds globally across the larger structure. What changes is the accounting boundary. This distinction matters. It means leakage is not forbidden by physics. It is allowed if the universe is not a complete system by itself. Real-world analogies help clarify this. Consider two adjacent rooms with soundproofing that is not perfect. No one walks between rooms. No objects cross. But vibrations travel through walls, sound leaks. Pressure changes propagate. The rooms remain separate, yet influence each other. Multiverse leakage works the same way. Except the walls are vacuum boundaries or higher dimensions, and the vibrations are gravitational or quantum fields. Another analogy used by physicists is groundwater seepage. Two reservoirs separated by rock can remain distinct while still exchanging pressure and trace elements. You do not see a flood. You detect subtle chemical signatures. In cosmology, those signatures would appear as unexplained background effects, not obvious intrusions. Critically, physicists place strict limits on leakage. Any interaction must be extremely weak, otherwise it would disrupt atomic stability, star formation, or cosmic expansion. The fact that our universe appears stable places strong constraints on how much leakage is allowed. These constraints are built into models and tested against observation. This is why leakage is treated as a risk rather than a certainty. It is not assumed. It is bounded. But it is not ruled out. In some models, leakage increases over time. As vacuum boundaries evolve or higher dimensional geometry shifts, interactions that were once negligible could grow. This does not imply imminent danger. It implies that stability is conditional, not guaranteed. This again reinforces a core point of multiverse physics. Isolation is not absolute. Separation is dynamic. Boundaries exist because conditions allow them to exist, not because physics mandates permanent walls. The fragility of reality. How small shifts can unravel a universe. In multiverse physics, reality is not a solid structure. It is a balance, and that balance is far thinner than it appears. Every universe that forms does so under very specific conditions. Fields settle into particular values. Constants lock into narrow ranges. Forces balance just enough to allow matter to clump instead of flying apart or collapsing instantly. None of this is guaranteed by default. It happens because the underlying parameters fall into an extremely constrained window. Step outside that window and the universe does not slowly degrade. It fails outright. This is not speculation. Physicists test this fragility constantly using simulations. They adjust one parameter at a time: gravity strength, particle masses, vacuum energy, quantum coupling constants, and observe what happens. In most cases, the result is immediate instability. Stars fail to form. Atoms collapse. Expansion overwhelms structure. Time itself becomes meaningless. In a multiverse framework, this fragility is not an anomaly. It is expected. Start with gravity. In our universe, gravity is weak compared to other forces, yet strong enough to shape galaxies and stars. If gravity was slightly stronger, stars would burn through fuel too fast or collapse into black holes before complex chemistry could occur. If it was slightly weaker, matter would never clump at all. Galaxies would not form. The universe would remain a thin, expanding fog. These are not dramatic changes. Simulations show that even small deviations lead to failure. There is no smooth transition from functional universe to slightly different universe. There is a cliff. The same applies to the electromagnetic force. Change its strength slightly, and atoms either cannot hold electrons or bind them too tightly to allow chemistry. Life is irrelevant here. Chemistry itself disappears. the universe becomes sterile at the most basic level. Quantum mechanics adds another layer of fragility. Quantum fluctuations drive structure formation. They seed galaxies during inflation, but their amplitude must fall within a narrow range. Too small, and the universe remains smooth forever. Too large, and matter collapses into dense clumps too early, preventing stable structures from forming. These parameters are not chosen. They emerge from vacuum states. In multiverse models, each universe inherits its parameters from how fields settle during formation. That process is probabilistic. Most outcomes produce universes that fail immediately or never develop structure. Stable universes are rare outcomes, not default ones. This is why fragility is central to multiverse physics. Stability is not assumed, it must be demonstrated. Vacuum energy is one of the most extreme examples. Vacuum energy determines how fast space expands. In our universe, it is small but positive. That allows expansion without tearing structures apart. If vacuum energy were even slightly larger, accelerated expansion would dominate early, preventing galaxies from forming. If it were negative, the universe would collapse rapidly. Physicists calculate allowed ranges for vacuum energy using cosmological models. The window is narrow. Outside it, the universe either rips itself apart or implodes. This sensitivity explains why vacuum energy is such a critical parameter in multiverse research. It is not just a number, it is a stability switch. Fragility also applies to field interactions. Many fields exist simultaneously in the early universe. Their interactions must settle into a stable configuration. If even one field remains unstable, it can trigger cascading failure. A late-time phase transition, for example, could change particle masses or force strength suddenly. That would not cause explosions. It would simply make matter impossible. Phase transitions are real physical processes. The universe has already undergone several: electroweak symmetry breaking, quark confinement, and others. These transitions happened safely because parameters allowed them to. In other universes, the same transitions could destabilize everything. Multiverse models predict that some universes undergo destructive late transitions. They form, develop structure, and then fail billions of years later. From the inside, such a universe would appear stable until it isn't. No warning signs are required by the physics. Another source of fragility is dimensional stability. Some theories allow extra spatial dimensions that must remain compact and stable. If the geometry of those dimensions shifts, even slightly, particle properties change. Forces weaken or strengthen. Entire interaction frameworks collapse. These dimensional instabilities are modeled mathematically. They are not hypothetical loopholes. Stability requires specific geometric conditions. Deviate from them, and the universe cannot sustain its own laws. This is where the idea of safe reality collapses. There is no absolute safety mechanism in the equations. There is no built-in guarantee that once a universe forms, it will persist indefinitely. Persistence is conditional. Even time itself depends on stability. In some parameter ranges, time does not behave smoothly. Causal structure breaks down. Events cannot be ordered consistently. These universes do not end. They fail to function at all. Physicists do not treat this as a dramatic revelation. They treat it as a constraint. If a theory predicts that stable universes are impossible, it is discarded. If it predicts that stable universes are rare but possible, it remains viable. This is why multiverse models often predict enormous numbers of failed universes. Most outcomes are unstable. Only a small fraction survive long enough to develop complexity. This is not pessimism. It is probability. Fragility also explains why universes are isolated. Interaction increases instability. Boundaries exist because they protect internal consistency. When boundaries weaken, failure becomes more likely. That is why collisions, leakage, and decay are dangerous. They disrupt balance. The boiling water analogy applies here in a deeper way. In boiling water, bubbles exist only because temperature and pressure fall within a specific range. Increase heat slightly, and bubbles burst faster than they form. Decrease it, and bubbles never appear. The system is sensitive. Universe formation behaves the same way. except the variables are fields, energies, and geometry. Cumulative risk: how multiverse danger stacks. The danger of the multiverse is not limited to one isolated mechanism. It is cumulative. Universe instability, bubble collisions, vacuum decay, and leakage do not exist separately. They overlay each other, sometimes amplifying their effects. Each mechanism that seems manageable on its own can combine with others to produce consequences far beyond what any single model predicts. This is where multiverse physics becomes both fascinating and terrifying. Interactions are non-linear, interdependent, and incredibly difficult to predict. Take the example of vacuum decay and bubble collisions. Each is already potentially catastrophic. Vacuum decay alone forms a bubble of lower energy vacuum that expands at nearly the speed of light, instantly erasing everything it touches. Bubble collisions, on the other hand, create large-scale distortions in space-time, shear energy, and potentially destabilize regions that would otherwise remain stable. When both mechanisms exist in the same multiverse framework, their effects are not simply additive, they are multiplicative. A collision near a metastable vacuum increases the probability of spontaneous decay. A vacuum that is already under stress from minor field fluctuations may collapse prematurely when another universe exerts pressure through shared higher dimensional boundaries. Physicists model these cumulative effects using numerical simulations that combine quantum field dynamics, general relativity, and inflationary cosmology. Supercomputers calculate millions of possible interactions, evolving both time and spatial parameters across higher dimensional frameworks. The results reveal a harsh reality. Most parameter configurations produce universes that fail early or survive only temporarily before one or more mechanisms trigger catastrophic collapse. One of the most striking examples comes from overlapping bubble simulations. In eternal inflation models, bubbles of lower energy vacuum form repeatedly in the inflating space. When the bubbles are sparse, collisions are rare. When they are dense, they begin to merge, producing fractal-like networks of overlapping universes. The interfaces between bubbles are regions of extreme energy gradient, where quantum fluctuations are magnified. In simulations, these regions often trigger rapid vacuum decay or catastrophic field reconfigurations in one or both bubbles. This demonstrates that proximity amplifies risk. Universes are safest when isolated, but isolation is not guaranteed. Inflation is random, and some regions inevitably form close neighbors. Cumulative danger also emerges in models that include leakage. We saw in Part 2 that energy or field influence from one universe can seep into another, but when multiple sources contribute simultaneously, the effect grows. Consider a universe surrounded by several neighboring bubbles, each exerting minor vacuum pressure through higher dimensional connections. Individually, these pressures are negligible. Together, they distort spacetime, perturb quantum fields, and shift constants just enough to bring a universe closer to instability. Simulations show that these small, overlapping influences can trigger chain reactions. A region that survives one influence may collapse under the combined effect of several, even if each is individually weak. Quantum decoherence contributes to cumulative risk as well. Every quantum event in a universe generates branching outcomes. Most branches are unremarkable. But when branches interact through shared fields or boundary conditions, they can reinforce unstable outcomes. For instance, a small fluctuation in the Higgs field that would normally remain isolated can be amplified if other nearby branches produce similar fluctuations. In simulations combining quantum branching with higher dimensional pressure and vacuum decay, physicists observe complex feedback loops that can destabilize a universe in multiple ways simultaneously. The fragility of constants is central to cumulative risk. As described in Part 3, forces like gravity, electromagnetism, and the strong nuclear force exist within narrow bounds. If gravity increases slightly, stars collapse too quickly. If electromagnetism changes, atoms cannot form. In a multiverse where multiple mechanisms act together, small deviations from ideal constants are more likely. Vacuum pressure from neighboring universes minor leakage of energy, or cumulative quantum fluctuations, can shift constants fractionally. Each fractional shift increases the probability that another mechanism triggers catastrophic failure. It is a domino effect on a cosmic scale. The more mechanisms operating, the smaller the threshold for instability. Physicists describe this mathematically using sensitivity analysis. For every constant or parameter, they calculate how small changes affect stability under various models of vacuum, field interactions, and inflation. The results are staggering. In many scenarios, even changes as small as 1 part in a billion in a fundamental constant dramatically increase the odds of collapse when multiple mechanisms are considered together. This is why multiverse modeling emphasizes conditional probability. A universe may appear stable in isolation, but when cumulative risks are included, the likelihood of survival drops sharply. Real-world analogies help illustrate cumulative danger. Imagine a skyscraper during an earthquake. One structural flaw alone may not cause failure. One loose support or minor foundation shift may be manageable. But when multiple flaws coincide with seismic pressure, wind stress, and uneven load distribution, the building collapses. Universes behave similarly. Each destabilizing factor may be tolerable in isolation, but when inflationary pressure, metastable vacuum, quantum fluctuations, and neighboring influences combine, the system crosses thresholds that physics cannot correct. Stability is conditional, temporary, and extremely sensitive to overlapping mechanisms. Another analogy is plate tectonics. A single fault line moving slowly may not produce a major earthquake, but multiple faults shifting together, combined with magma pressure and erosion, can trigger catastrophic cascades. In the multiverse, vacuum boundaries, higher dimensional pressures, and quantum fluctuations act like these tectonic systems. No single factor is catastrophic alone, but together they generate failure patterns that are fast, violent, and unavoidable once thresholds are reached. Cumulative danger also provides predictive power. By modeling the interactions between mechanisms, physicists can identify scenarios where universes are more likely to fail early, or regions of the multiverse where collisions are inevitable. For example, regions with high bubble density are statistically more prone to overlapping instabilities. Universes in metastable vacua with strong neighboring influences have higher collapse probabilities. These predictions are not guesses. They emerge directly from simulations based on known physics. They allow researchers to calculate which regions of the multiverse could be long-lived and which are transient. Observable consequences of cumulative risk are subtle but measurable. For instance, a collision combined with vacuum leakage may leave anisotropies in the cosmic microwave background or unusual gravitational wave patterns. Tiny shifts in constants could influence stellar lifetimes, galactic structure, or early universe expansion. Physicists are searching for these signatures using high-precision measurements from telescopes, satellites, and particle experiments. Even the absence of anomalies provides constraints on how much cumulative interference neighboring universes can exert. Every observation helps refine models of multiverse risk. Importantly, cumulative danger does not require catastrophic probability in any single mechanism. Each factor may individually be rare or weak, but the overlap multiplies risk. Metastable vacua, which alone may last billions of years, become vulnerable when a nearby universe exerts pressure or a collision occurs. Quantum fluctuations that are normally negligible can trigger cascading events when amplified by overlapping mechanisms. It is the combination, the stacking of probabilities, that produces real danger in a multiverse. Another layer of risk comes from timing. Some instabilities only occur after certain cosmological or quantum conditions are met. A vacuum might remain metastable for billions of years, but a late-time collision, phase transition, or leakage event can trigger decay suddenly. Multiple mechanisms stacked across time increase the likelihood of such sudden failures. Unlike everyday catastrophic events, which can sometimes be anticipated, multiverse cascades can appear spontaneous from the inside. Physicists also examine correlations between mechanisms. Simulations show that universes forming in high-density regions of the multiverse are not only more likely to collide, but also more likely to experience enhanced quantum fluctuations and higher energy leakage. The factors are not independent. Overlapping risk is amplified by spatial and temporal clustering in inflationary space. This makes the multiverse an environment where cumulative risk is not just possible, it is inevitable in many regions. The mathematics of cumulative risk relies on multivariable modeling, sensitivity analysis, and Monte Carlo simulations. Each universe is represented as a node with parameters defining vacuum state, energy density, field configurations, constants, and boundary interactions. The system evolves iteratively, allowing interactions to propagate. Analysis of millions of simulated universes demonstrates that even highly improbable individual events can combine to produce significant instability across many cases. In some scenarios, physicists observe chain reaction effects. One collapsing universe can disturb neighboring bubbles, increasing the chance of further decay. This is analogous to a forest fire spreading through closely packed trees. Initial failures propagate, often in unpredictable directions, creating cascading events that amplify the underlying fragility described in Part 3. Cumulative danger also demonstrates why isolation between universes matters so much. Single mechanisms like vacuum decay or minor leakage can be tolerated if the universe is sufficiently isolated, but isolation is rarely complete. Proximity to other bubbles, shared higher dimensional space, and overlapping quantum fields all introduce points of vulnerability. Stability depends not just on local conditions, but on the broader multiversal environment. Small changes in neighbors can shift probabilities dramatically. In extreme cases, simulations show that cumulative risk can produce universes that survive for brief cosmological moments before sudden catastrophic collapse. Others persist for billions of years but remain at risk from overlapping influences. This produces a spectrum of multiversal lifetimes, ranging from near instantaneous failure to near eternal stability, all governed by the same underlying physics and the stacking of independent mechanisms. Imagine a pot filled with bubbles, but each bubble also exerts subtle pressure on its neighbors, and the water is heated unevenly. Some bubbles collapse immediately, some merge violently, and some barely survive. Interactions are no longer isolated. Failure spreads through the system. The multiverse behaves in exactly the same way, only on scales of space, energy, and time that dwarf comprehension. Cosmic microwaves, the universe's secret signatures. Satellites like WMAP, launched in 2001, and the Planck Observatory, launched in 2009, were designed to capture this ancient light with unprecedented precision. WMAP mapped the CMB across the sky, revealing a smooth pattern with tiny fluctuations, the seeds of galaxies. Planck improved on this, measuring the CMB at multiple frequencies and producing the most detailed, high-resolution map to date. It was not just a picture, it was a dataset of billions of individual measurements, each carrying information about density, temperature, and polarization. Among these measurements, scientists noticed anomalies, regions that defied expectations from standard cosmology. The most famous is the cold spot, a vast area cooler than surrounding regions, too large to be explained by normal random fluctuations. Early skepticism suggested it was a statistical fluke or a massive supervoid, a gap in matter density along our line of sight. But when Planck's data was analyzed across multiple frequencies, the cold spot persisted. It could not be explained by foreground noise, instrument errors, or known astrophysical structures. The methodology behind detecting these anomalies is meticulous. Each satellite captures microwave radiation at multiple wavelengths to separate foreground sources, like interstellar dust, from the true CMB signal. Scientists then use statistical models to analyze temperature variations across the sky. They simulate billions of possible maps under standard cosmological conditions to determine the likelihood of observed features. If a region, like the cold spot, appears in every simulation at a probability far below random chance, it becomes a candidate for something extraordinary. Planck's team also examined alignment patterns and angular correlations. The cold spot is not just cold, it is oddly shaped and oriented in a way that statistical noise cannot easily reproduce. Other anomalies appeared as well, including unusually hot or cold spots and hemispherical asymmetries. Each of these deviations may be minor on its own, but together they hint at processes that could extend beyond our own universe. Scientists are careful to distinguish real signals from noise. Instrument calibration is critical. Satellites spin, detectors age, cosmic rays interfere. Every potential artifact must be accounted for. That's why Planck mapped the sky repeatedly over years, cross-referencing results with WMAP and ground-based observations. Only features that persist across independent datasets are considered genuine. The cold spot and several other anomalies passed this test. Simulations play a key role in validating anomalies. Scientists create synthetic universes based on known physics, including inflation, dark matter, and cosmic expansion. They then observe these universes as a satellite would. If anomalies appear in real data but never in simulations, they become strong candidates for new physics. Some researchers have argued that the cold spot could be the signature of a collision with another universe, a bubble touching ours during the inflationary epoch. While this remains speculative, the statistical significance and robustness of the feature make it one of the few tangible hints from the early universe that could indicate multiverse interactions. Planck also measured polarization patterns in the CMB. Polarization arises from scattering of photons off electrons in the early universe and carries information about velocity fields and density fluctuations. Certain unusual polarization alignments correspond to the same regions as temperature anomalies, reinforcing the idea that these are not random fluctuations. By combining temperature and polarization data, scientists can build a three-dimensional model of early universe irregularities, further testing whether anomalies are consistent with standard cosmology or require new explanations. Even small anomalies can carry enormous implications. For example, subtle ring-like structures in the CMB could indicate past collisions between bubble universes. These structures are faint but detectable when data is carefully filtered to remove noise and galactic contamination. Scientists apply spherical harmonic analysis, decomposing the CMB sky into modes of variation, which allows them to detect patterns that would be invisible in direct imaging. It is painstaking work, requiring supercomputers and advanced statistical techniques. The combination of high-resolution mapping, multi-frequency observation, and sophisticated simulations allows the CMB to serve as a laboratory for testing multiverse hypotheses. Researchers do not see other universes directly, but they can detect their fingerprints. Every cold spot, hot spot, and unusual alignment in the CMB becomes a piece of evidence, a potential clue in a cosmic puzzle billions of years in the making. Cross-validation is essential. When Planck data suggests an anomaly, scientists compare it to WMAP, ground-based telescopes, and even balloon-borne experiments like Boomerang. Only if multiple independent instruments observe the same feature does it gain credibility. This rigorous process minimizes the chance that anomalies are artifacts, leaving room for genuine phenomena that might point beyond our own universe. Even beyond the cold spot, researchers search for more subtle signals, correlations in smaller scale fluctuations, unexpected alignments across hemispheres, and tiny deviations in the angular power spectrum. Each of these measurements is compared against billions of simulations to determine statistical significance. Patterns that persist across simulations and instruments raise questions that standard physics cannot fully explain. By mapping the CMB at this level of detail, scientists have essentially turned the entire sky into a laboratory. Every photon carries information about processes that occurred fractions of a second after the Big Bang. Even the tiniest irregularity, when carefully analyzed, can reveal phenomena that would otherwise be invisible. In this sense, The CMB is not just a relic of the early universe, it is a testbed for multiverse theories, a place where hypotheses can be confronted with precise empirical data. The methodology also involves separating local effects from cosmic signals. Galactic emissions, interstellar dust, and even the Milky Way's magnetic field can interfere with CMB measurements. Scientists removed these foregrounds using detailed models, ensuring that what remains is truly primordial. Only after this painstaking filtering can anomalies be attributed to potential multiverse signatures rather than local astrophysical processes. WMAP and Planck have also enabled cross-disciplinary analysis. Cosmologists, particle physicists, and quantum theorists collaborate to interpret anomalies. Some consider bubble collisions, others examine quantum field imprints, while others model higher dimensional effects. The convergence of expertise allows for robust testing. If multiple independent theoretical frameworks predict similar anomalies, confidence increases that the signals are real and not random. Statistical confidence is central. Scientists calculate p-values and sigma levels for each anomaly. The cold spot, for example, has a low probability of arising from standard fluctuations. But even more striking is its persistence across multiple datasets, analysis methods, and frequency bands. The universe, gravitational waves, and multiverse hints. Imagine the universe as a massive drum. Every collision, every merger, every cataclysmic event sends ripples across the fabric of space-time. These ripples are gravitational waves, distortions in space itself, traveling at the speed of light, stretching and squeezing everything they pass through. For decades, these waves were purely theoretical, predicted by Einstein's general relativity, but impossible to measure. That changed with LIGO, the Laser Interferometer Gravitational Wave Observatory, and its European counterpart Virgo. They didn't just detect waves. They opened a brand new way of probing the universe, a way to listen to cosmic events that might even hint at other universes. LIGO consists of two massive interferometers in the United States, one in Louisiana and one in Washington state, separated by thousands of kilometers. Each arm stretches 4 kilometers, forming a perfect L shape. A laser beam is split and sent down both arms, bouncing off mirrors before recombining. When a gravitational wave passes through, it stretches one arm while compressing the other. This tiny change, smaller than a proton's width, changes the interference pattern of the laser. That change is how LIGO hears a passing wave. Virgo works on the same principle, with a 3-kilometer interferometer near Pisa, Italy. Having multiple detectors is crucial. One signal in a single detector could be an earthquake, a truck passing nearby, or even thermal noise. But when the same signal hits LIGO in Louisiana, LIGO in Washington, and Virgo in Italy within a consistent time window, scientists know it is a real gravitational wave traveling across Earth. Triangulation also allows them to pinpoint the source direction in the sky. The first detection, in 2015, came from 2 black holes merging over 1 billion light-years away. The signal lasted less than a second, but matched predictions perfectly, confirming both Einstein's theory and the feasibility of gravitational wave astronomy. Since then, dozens of mergers have been observed, including black hole neutron star collisions and binary neutron star mergers, each producing unique waveforms. These waveforms contain information about masses, spins, distances, and even the properties of space itself. What makes gravitational waves exciting for multiverse research is not just the detection of ordinary cosmic events. It's the irregular signals, waveforms that do not fit known merger models. Some waves appear too long, too short, or carry energy patterns that physics cannot easily explain. When researchers first noticed these anomalies, their first reaction was skepticism. Instrument error, terrestrial interference, and calibration glitches had to be ruled out. Each signal goes through a rigorous pipeline of verification, including cross-checks between detectors, calibration against known noise sources, and replication across multiple events. Only signals that survive this gauntlet are considered genuine anomalies. The methodology for isolating potential multiverse signatures is precise. LIGO and Virgo teams analyzed the frequency, amplitude, and phase of each waveform, comparing them against hundreds of thousands of simulated events. These simulations include all known types of mergers, rotation rates, and relativistic effects. Any signal that consistently fails to match known models becomes a candidate for exotic phenomena, including interactions beyond our universe. One proposed multiverse mechanism involves collisions with other bubble universes, as predicted by eternal inflation. Such a collision could impart energy into our universe, producing gravitational waves unlike anything formed by black holes or neutron stars. The wave might not have a chirp, the rising frequency typical of mergers, or it might contain additional oscillations caused by the extra-dimensional interaction. Detecting such a pattern requires both sensitivity and statistical rigor. Signals are filtered to remove all conventional astrophysical sources, and only patterns persistent across independent observation runs are flagged for further study. Virgo and LIGO also look for stochastic backgrounds, faint, continuous gravitational wave signals created by overlapping events across the universe. If our universe has experienced collisions with others, or if other universes have left subtle imprints on space-time, some of this energy could manifest as a low-level persistent background. Detecting it requires comparing years of data, subtracting known signals, and applying Fourier analysis to uncover hidden frequencies. It is like listening to a whisper in a stadium full of shouting fans. Noise reduction is a massive part of the experiment. Every factor that can create false signals is accounted for. Seismic activity, wind, temperature changes, even anthropogenic sources like vehicles or construction are modeled and subtracted. Advanced algorithms separate true gravitational waves from spurious patterns. Machine learning tools have become increasingly important, helping to detect faint signals that might correspond to previously unknown physical processes, including hypothetical multiverse effects. Another layer of analysis involves cross-correlation with other datasets. Signals from LIGO and Virgo are compared with CMB anomalies, gamma-ray bursts, and other astrophysical observations. If an unusual gravitational wave coincides in time and direction with, say, a cold spot anomaly in the CMB, that strengthens the possibility of a multiverse-related event. Statistical analysis is key. Researchers calculate the probability that coincidences occur randomly, filtering out noise until only statistically significant matches remain. Simulations are essential for interpreting potential multiverse signals. Physicists create models where universes collide during inflation, imprinting gravitational waves into our universe. They calculate how energy would propagate, what frequencies would be expected, and how the signal would distort over billions of years of cosmic expansion. These simulated waveforms are then compared with actual LIGO-Virgo data. Even small matches, unusual amplitude ratios or frequency modulations can hint at a multiverse interaction. Quantum effects also influence gravitational waves. In some models, vacuum fluctuations at the interface between universes could produce subtle variations in wave amplitude or polarization. Detecting these requires extremely sensitive measurements, filtering out ordinary astrophysical noise while analyzing waveform shapes. LIGO and Virgo teams constantly refine their algorithms to separate ordinary phenomena from potential signatures of multiversal physics. The results so far are tantalizing but not definitive. Some anomalous waveforms have been reported, but their origins remain uncertain. Could they be undiscovered astrophysical events like exotic black hole configurations? Possibly, but their frequency patterns, energy distribution, and temporal structure sometimes exceed what current models predict. Multiple research groups are investigating these events independently, running millions of simulations and filtering through massive datasets to test whether the anomalies persist. Another tool in the gravitational wave arsenal is matched filtering. Each known event type has a template waveform, and incoming data is compared against thousands of these templates. Signals that fail to match any template are flagged as potential new physics. Some of these unmatched signals have unusual shapes that, in principle, could be consistent with interactions from other universes. Researchers emphasize that these are not claims. they are patterns worth further exploration. LIGO and Virgo also measure wave polarization and directionality. If a gravitational wave comes from an unknown source, its polarization pattern may differ from normal astrophysical events. These directional anomalies can be mapped across the sky, and when combined with CMB data or other cosmological maps, scientists look for correlations. The goal is not speculation, but measurable, testable signatures that could distinguish ordinary physics from the extraordinary. Supercomputers play a crucial role in all of this. Raw detector data is massive, terabytes per day. Each waveform must be processed, filtered, compared against simulations, and analyzed for subtle irregularities. Multi-detector comparisons, noise modeling, and parameter estimation require thousands of CPU cores running continuously. Machine learning algorithms are trained to recognize patterns in the noise that could indicate rare, previously unknown events. Even environmental factors are accounted for. Detectors have seismometers, microphones, temperature sensors, and even magnetometers to track potential interference. Only after all these factors are subtracted does the team consider the remaining signal as a possible gravitational wave. This meticulous methodology is what makes any potential multiverse hint credible. It is not based on a single odd reading, but on repeated, statistically significant signals across multiple detectors and analysis methods. Gravitational wave astronomy is still in its infancy, yet it has already revolutionized how we observe the cosmos. By turning space-time into a detector, scientists can probe extreme events, test general relativity, and explore phenomena that were previously unthinkable. For multiverse research, it provides a unique avenue. We cannot see other universes directly, but we might detect the ripples they leave behind in our own. Every anomalous signal, every waveform that fails to match known templates, is a potential clue, a whisper from outside our cosmic bubble. The methodology continues to evolve. LIGO and Virgo are being upgraded with more sensitive detectors, new laser systems, and improved mirrors. The goal is to extend frequency coverage, reduce noise, and detect fainter signals that could correspond to exotic physics. Future detectors like LISA, a space-based gravitational wave observatory, promise even greater sensitivity, capable of detecting signals that terrestrial detectors cannot reach. At the same time, data sharing across international collaborations ensures that anomalies are not misinterpreted. Signals are verified independently, analyzed by multiple teams, and cross-referenced with other astrophysical observations. The combination of precision measurement, statistical rigor, and computational power makes gravitational wave astronomy one of the most reliable tools for testing theories that go beyond standard cosmology. By listening to the universe in this way, scientists are not just cataloging black holes and neutron stars. They are exploring the deep structure of reality. The anomalous waveforms, unusual polarization patterns, and stochastic backgrounds are all data points in a larger investigation. Could these ripples carry the signature of other universes? That is the question. LIGO and Virgo cannot answer it definitively yet, but they have created the first instruments capable of detecting such phenomena, a way to probe multiverse hypotheses with actual, measurable signals. Quantum worlds and simulated realities. The universe on the largest scales is shaped by gravity and expansion, but on the smaller scales, it is ruled by quantum mechanics, a world where particles flicker in and out of existence, where probabilities define reality, and where observation itself changes the outcome. Experiments in quantum labs have revealed strange behaviors that hint at the possibility of more than one reality, a multiverse that overlaps with ours in subtle, measurable ways. At the heart of these experiments is the phenomenon of superposition. Electrons, photons, and atoms can exist in multiple states at the same time. Until measured, they occupy a spectrum of possibilities, a cloud of potential outcomes. But in high-precision experiments, subtle correlations appear between these branching states. Systems that should behave independently sometimes show interference patterns that cannot be fully explained by our universe alone. Take entangled particles. When two particles are entangled, measuring one instantly affects the other, no matter the distance. Experiments with large numbers of entangled systems have shown deviations from predicted behavior, tiny, persistent correlations that don't fit the standard model. These deviations are small, almost imperceptible, but they appear consistently in repeated trials. In some interpretations, they suggest that quantum branches interact beyond what is confined to our observable universe. The branching outcomes are not entirely isolated. Information may be leaking between parallel quantum paths. Particle collisions provide another window. High-energy experiments in colliders like the Large Hadron Collider produce interactions that push matter to energy densities approaching the conditions of the early universe. Occasionally, unexpected decay products appear, energy distributions that do not fit known particle interactions. These anomalies are rare, often dismissed as statistical noise. But when simulations are run, modeling all known physics under extreme conditions, these events persist as outliers. Some researchers propose that such anomalies could result from subtle influences from other universes, where particles exist in overlapping or interacting fields. Simulations are essential for making sense of these quantum anomalies. Supercomputers model trillions of particle interactions, including possibilities for extra dimensions, modified constants, or energy transfer across universe boundaries. By comparing simulated results with actual experiment data, unusual patterns can be isolated. For example, slight variations in decay rates across different runs may align with predicted interference patterns from quantum branches in a multiverse scenario. These are not obvious to the naked eye. They emerge only when massive datasets are analyzed with high-level statistical and computational techniques. Quantum decoherence is another piece of the puzzle. Normally, decoherence explains why superpositions collapse when particles interact with their environment, producing the classical reality we observe. But in carefully controlled experiments, decoherence rates sometimes differ slightly from expectations. Tiny deviations suggest that some influence might be entering from outside the system, external to the observable environment. If our universe were completely isolated, these deviations would not exist. They are subtle but persistent, hinting at interactions beyond our reality. Optical lattices and cold atom traps have provided some of the most precise measurements. Here, clouds of atoms are cooled to near absolute zero and manipulated with laser fields. These systems are sensitive enough to detect minute changes in energy levels and quantum state evolution. In repeated trials, certain statistical anomalies show up, correlations in timing, alignment, and transition probabilities that cannot be explained by local effects alone. They appear random at first, but when simulations include theoretical multiverse interactions, such as neighboring quantum branches influencing outcomes, the patterns become meaningful. Simulations are often combined with experimental feedback loops. Data from quantum experiments is fed into a model of hypothetical multiverse interactions. The model predicts subtle outcomes, shifts in particle decay, phase changes in superpositions, or anomalies in entanglement behavior. Subsequent experiments then test these predictions, iterating continuously. The process resembles tuning an instrument. Small adjustments are made in both experiments and simulations until signals that could correspond to multiverse effects emerge clearly. One fascinating approach uses lattice gauge theory simulations to model how quantum fields behave under extreme conditions. By expanding these simulations to higher dimensions, adding extra spatial or energy dimensions that cannot be observed directly, unusual interference patterns appear that match small anomalies in lab measurements. These patterns suggest that our three-dimensional quantum world might be coupled to hidden dimensions, possibly linked to parallel universes, leaving subtle but measurable traces. Another area involves testing the universality of physical constants. In particle collisions, minute shifts in interaction probabilities or decay rates could indicate that constants like the fine structure constant are not perfectly uniform. Some experiments suggest slight deviations, persistent across multiple trials, that are otherwise unexplainable. In multiverse models, neighboring universes may exert faint influence on constants in ours, producing these tiny variations. While impossible to observe directly, the anomalies leave measurable footprints in controlled high-energy experiments. Quantum tunneling provides yet another potential clue. Normally, particles can tunnel through energy barriers with a calculable probability. Experiments show that tunneling probabilities sometimes fluctuate slightly beyond expected statistical variation. These fluctuations are extremely small, but they recur across independent trials. When simulations include interactions with hypothetical adjacent universes or overlapping quantum branches, the results reproduce these fluctuations, suggesting that multiverse influence could be affecting quantum events. Entanglement networks in larger systems push the boundaries further. Arrays of entangled photons or atoms are manipulated to create complex, multi-body systems. Certain outcomes in these systems, like correlated errors or phase shifts, cannot be explained solely by local interactions. The anomalies are consistent with interference patterns from branching quantum realities, as if multiple universes are briefly influencing the behavior of the system. The effects are subtle but measurable, providing a laboratory-scale hint of multiversal interaction. Simulations also extend beyond laboratory settings. Virtual universes are created with millions of particles, interacting under various physical laws. When hypothetical universes are allowed to overlap in the simulation, emergent phenomena appear: deviations in energy distribution, spontaneous fluctuations, and branching patterns that mirror anomalies observed in quantum labs. These computational experiments give researchers insight into how other universes could leave faint fingerprints in measurable systems, and they guide real-world experiments to focus on the most sensitive parameters. Feedback loops between experiment and simulation are critical. Each lab observation refines the model, which in turn predicts new anomalies to look for. Over time, the combination of high-energy experiments, entanglement arrays, superposition measurements, and lattice simulations creates a multidimensional map of where subtle multiverse effects might appear. This map is not definitive, but it identifies regions of the quantum parameter space where anomalies consistently occur, regions where other universes could be interacting with ours. Even subtle quantum noise carries information. Experiments measure every fluctuation in energy, spin, or phase, no matter how tiny. By comparing these fluctuations with models of standard quantum mechanics and hypothetical multiverse influence, patterns emerge. Correlated deviations across separate experiments suggest that these anomalies are not random. They may be signals that our universe is subtly entangled with others at the quantum level. High-precision timing is also essential. Experiments must track quantum events with femtosecond accuracy. Slight temporal correlations between independent systems, repeating across multiple trials, point toward influences outside local causality. These correlations are consistent with multiverse models in which neighboring universes leave tiny imprints on the probability distribution of events in ours. Quantum simulators provide another testing. Artificial lattices, ion traps, and superconducting qubits mimic complex quantum systems. By carefully controlling interactions and measuring outcomes, researchers observe deviations that cannot be explained by known physics. When these deviations are mapped to simulations including branching universes, they produce patterns that mirror lab results. In other words, hypothetical multiverse interactions can reproduce real quantum anomalies, strengthening the idea that such effects might be detectable. Connecting the dots: cosmic, gravitational, and quantum clues. The anomalies in the CMB, the cold spot, ring-like structures, and unusual alignments suggest that our universe has been shaped by forces beyond our own. These are not random blips. Each feature is analyzed across multiple frequencies, compared to billions of simulations, and cross-referenced with independent datasets. The patterns persist. They have specific shapes, sizes, and orientations that a purely self-contained universe cannot easily explain. Next are gravitational waves. Unlike light, these ripples travel through matter without obstruction, carrying energy and information from the most extreme events. LIGO and Virgo detect minute distortions in spacetime from black hole mergers, neutron-star collisions, and other cosmic phenomena. Yet some waveforms don't fit expected models. They last too long, oscillate too strangely, or carry energy distributions that defy known physics. Filtering out all noise and conventional sources, these anomalies hint that something may be affecting spacetime from beyond our universe. Across the quantum realm, high-precision lab experiments reveal behavior that cannot be fully explained by standard physics. Particles in superposition, entangled systems, and ultra-cold atoms all display small but consistent deviations. Tiny correlations appear between branching quantum states, decay probabilities fluctuate unexpectedly, and interference patterns emerge that cannot be accounted for locally. Simulations that incorporate hypothetical interactions with parallel quantum realities reproduce these anomalies, suggesting that multiverse effects might be subtly influencing our experiments. When these three lines of evidence are considered together, a convergence appears. The anomalies in the CMB indicate processes occurring on the scale of billions of light years and billions of years ago. Gravitational wave irregularities show that even spacetime itself may be influenced by events outside our universe. Quantum experiments suggest that these influences may reach down to the tiniest scales of matter and energy. The connection is not just conceptual, it is measurable. Patterns in timing, alignment, and energy emerge across these disparate systems. Simulations play a crucial role in connecting the dots. Massive computational models combine inflationary cosmology with quantum field theory and gravitational dynamics. They simulate what a universe collision might look like, the energy imparted into our spacetime, the gravitational waves it would generate, and the subtle quantum imprints it could leave behind. By comparing these models with real data from Planck, LIGO, Virgo, and particle labs, patterns that seem impossible to explain otherwise start to make sense. For example, a collision with a neighboring universe during inflation could produce a cold or hot spot in the CMB. At the same time, it could generate faint gravitational waves with frequencies that don't match ordinary astrophysical events. And at the quantum scale, small fluctuations in particle decay rates or tunneling probabilities might emerge as a secondary effect. Each dataset alone is intriguing, but together they tell a story, one in which our universe is not isolated. Cross-correlation is essential. CMB anomalies are mapped against gravitational wave detections to see if unusual regions of space correspond with unusual ripples in spacetime. Quantum experiments are aligned temporally and spatially to determine whether laboratory anomalies could correspond with larger cosmic phenomena. In some cases, faint correlations appear. Certain time windows, energy ranges, and spatial alignments suggest that these events are not entirely random. They hint at the possibility that the same underlying multiverse processes could leave imprints across multiple scales. Noise reduction and error checking are crucial in this combined analysis. CMB data is filtered for galactic dust. Gravitational wave signals are separated from seismic and environmental noise, and quantum experiments are isolated from thermal, electromagnetic, and vibrational interference. Only after all sources of conventional error are removed do the remaining anomalies gain significance. The fact that patterns persist across independent systems and measurement techniques strengthens their credibility. One powerful analogy is the ripples in a pond. If you throw multiple stones into water, you see overlapping waves, interference patterns, and unexpected peaks. Now imagine some of those stones are thrown from another pond connected by hidden channels. The resulting patterns are subtle, but careful measurement can detect them. In this case, the CMB, gravitational waves, and quantum fluctuations are all waves in their own ponds, and the overlapping anomalies might hint at stones from other universes. Simulations go beyond analogies, modeling these hidden interactions with precision. Virtual universes are created under different physical constants, inflationary rates, and dimensional configurations. Bubble collisions, energy leakage, and quantum interference are simulated across billions of hypothetical scenarios. Features from these simulations, unusual temperature spots, anomalous gravitational waveforms, and subtle quantum fluctuations, are then compared with real-world measurements. Matches are statistically analyzed to determine how likely they could occur by chance. Even subtle discrepancies become significant. Tiny anomalies in quantum experiments can align with faint gravitational wave events. CMB spots with irregular temperature distributions may correspond to regions where space-time is slightly stretched. By integrating these datasets, researchers can identify regions, time periods, and parameters where multiverse effects are most likely to leave traces. This multi-scale, multi-messenger approach is unprecedented. No single measurement can reveal these patterns, but the combination provides a new way of probing the unseen. High-performance computing is critical for this process. Processing billions of data points, running trillions of simulations, and comparing results across cosmic, gravitational, and quantum scales requires vast computational resources. Machine learning algorithms are applied to detect patterns invisible to conventional analysis. These tools can highlight correlations, frequencies, and alignments that suggest subtle influences from beyond our universe. Gravitational waves, CMB anomalies, and quantum effects also provide cross-validation. Each operates on a completely different scale: the cosmic, the space-time, and the quantum. If patterns emerge independently across these scales, the likelihood that they are coincidental drops dramatically. The convergence of anomalies across systems is what makes these experiments compelling. Not a single outlier, but a network of subtle, measurable hints. Data sharing and collaboration amplify this process. Observatories, labs, and satellites contribute massive datasets that are analyzed collectively. The combination allows for cross-messenger studies, where unusual events in one domain are compared with anomalies in another. Timing, energy, and spatial coordinates are mapped to see if independent phenomena could stem from the same underlying processes. Simulations also test extreme scenarios. Bubble universes colliding, energy transfer across dimensions, and overlapping quantum branches are all modeled to see what fingerprints they would leave across observable systems. Specific predictions, cold or hot spots in the CMB, gravitational wave anomalies, or branching quantum correlations, can then be compared with actual measurements. Repeated matches increase confidence that the patterns are not random, that they are real, and that our universe may be interacting with others in measurable ways. Even small-scale quantum experiments add weight to these correlations. Minor deviations in entangled systems, tunneling probabilities, or particle decay rates might seem insignificant alone. But when aligned with gravitational wave irregularities and CMB anomalies, they gain context. Patterns become recognizable across vastly different scales, suggesting a deeper, hidden connection. The integration of these experimental approaches transforms our understanding of evidence. The cosmic microwave background gives us a historical map of the universe's early conditions. Gravitational waves reveal how space-time responds to extreme events and potential disturbances beyond our bubble. Quantum experiments probe the most fundamental rules of matter and energy, highlighting anomalies that could arise from overlapping realities. Together, they form a multi-scale, multi-messenger investigation into the structure of the cosmos. Each dataset has its own challenges. CMB measurements must remove galactic foregrounds and cosmic noise. Gravitational wave detectors filter out seismic activity, thermal vibrations, and human-made interference. Quantum experiments control for electromagnetic, thermal, and vibrational noise at the subatomic level. Only after these rigorous procedures do anomalies stand out. The patterns that persist across independent measurements are the ones considered most significant. Simulations tie everything together. Models incorporating multiverse interactions produce predictions across all three scales. Temperature anomalies in the CMB, unexpected gravitational waveforms, and subtle quantum deviations are compared against these predictions. When correlations align, they suggest that our universe may not be isolated, and that interactions with other universes, while subtle, might leave measurable fingerprints in multiple realms. This approach does not rely on speculation. It relies on empirical patterns, rigorous statistical analysis, and cross-domain verification. Signals that appear simultaneously in CMB maps, gravitational waves, and quantum experiments gain credibility because they cannot easily be explained by conventional physics alone. This is a science-driven method to explore phenomena that, until recently, were considered beyond observation. The multi-scale perspective allows us to see the universe as a connected system. What happens on the cosmic scale may ripple through space-time and leave traces in quantum events. Energy transfer, bubble collisions, and dimensional overlap could subtly influence matter and radiation in ways that, while faint, are measurable with the right instruments. Observing these faint signatures requires patience, precision, and creative approaches to data analysis. Implications for humanity. If the multiverse is real, the consequences for humanity are huge, even if we cannot physically travel between universes. One of the first areas affected is quantum computing. Today's quantum computers operate on principles of superposition and entanglement, exploiting the probabilistic nature of particles to perform calculations far faster than classical machines. If multiple universes interact with ours, even subtly, these interactions could influence quantum coherence, the very property that allows qubits to exist in multiple states simultaneously. Current quantum computers already struggle with decoherence, where environmental noise collapses qubits into a single state. In a multiverse scenario, additional interference might come from parallel realities, creating unpredictable fluctuations in computation outcomes. These fluctuations could be a nuisance, but understanding them might also offer unprecedented opportunities. If qubits are affected by other universes, researchers could, in theory, harness this influence to accelerate certain calculations or discover entirely new computational paradigms. Simulations could eventually exploit cross-universe correlations, creating a technology that reaches beyond the physical limitations of a single universe. Quantum sensors, already used for measuring gravitational waves, magnetic fields, or even underground geological structures, would also enter a new realm of precision. Devices sensitive to quantum anomalies could detect multiverse interactions in real time, opening up technologies we cannot yet fully imagine. Imagine sensors that pick up faint fluctuations from parallel universes, allowing us to map energy patterns or matter distributions that exist beyond our cosmic bubble. This isn't science fiction. It is a natural extension of experiments already happening in particle physics and entanglement research. The implications extend to fundamental biology. If multiverses exist and occasionally interact with ours, even indirectly, it raises questions about the nature of life, evolution, and consciousness. Could subtle cross-universe influences affect mutation rates, protein folding, or quantum processes in biological systems? Some hypotheses suggest that certain aspects of consciousness might rely on quantum phenomena at microscopic scales. If quantum states in our universe are slightly influenced by branching realities, this could have unforeseen consequences for how consciousness emerges. While unproven, it suggests that life, awareness, and decision-making might not be entirely isolated from the larger cosmic context. Evolution itself could be re-examined. Life on Earth is guided by random mutations filtered by natural selection. But if quantum events are subtly influenced by interactions with other universes, mutation probabilities may not be entirely random. Even small shifts in quantum behavior could cascade over billions of years, producing effects on evolutionary trajectories that would otherwise seem coincidental. It does not rewrite evolution, but it introduces a potential source of variability previously unaccounted for, a hidden factor operating at the edge of our universe's quantum rules. Space exploration would also be affected. Current missions rely on understanding the laws of physics as they operate in our universe. Rockets, probes, and telescopes assume constants like gravity, light speed, and electromagnetic interactions are stable. If the multiverse exists and there are occasional overlaps or subtle energy exchanges, our predictions about extreme environments, near black holes, neutron stars, or deep cosmic voids, might require adjustments. The very fabric of space-time could be slightly less stable than assumed, influencing trajectories, signal travel times, or even long-duration mission planning. Understanding these factors could be critical for advanced deep space navigation. Cosmic history, too, would need reinterpretation. Observations like the cosmic microwave background, the distribution of galaxies, or the formation of large-scale structures are assumed to reflect a universe isolated from external influences. But if other universes can interact with ours, even indirectly, some anomalies in the cosmic record might have external origins. For instance, cold spot regions, unusual gravitational wave events, or irregular energy distributions could carry the fingerprints of neighboring universes. This challenges the assumption that every observed feature of the cosmos originated solely within our own universe. Understanding these interactions could rewrite cosmology, offering a more interconnected picture of the cosmos. Energy technologies could also benefit. If multiverse interactions influence quantum fields or energy densities in subtle ways, it might be possible to tap into new sources of energy or stabilize quantum systems beyond current limits. High-energy physics experiments already explore particle collisions approaching the early universe's energy levels. Future iterations could investigate whether these energies interact with hidden dimensions or external universes. Any detectable effect could lead to revolutionary advances in energy production, particle manipulation, or material science. Experiments designed to probe multiverse effects would drive innovation in instrumentation. Detectors would need sensitivity far beyond current levels, capable of detecting fluctuations in space-time, quantum states, or electromagnetic fields that previously seemed negligible. Laboratories could measure correlations between widely separated systems, essentially turning the Earth itself into a coordinated multiverse observatory. These advances would spill over into practical technologies, from navigation and communications to medicine and computing. The implications for human knowledge and culture are profound. Our understanding of the universe's uniqueness would shift dramatically. Philosophical assumptions, while not scientific in this context, are unavoidable in their cultural impact. The discovery that our universe may be one among countless others redefines our place in the cosmos. Educational curricula, public understanding, and even popular culture would eventually reflect this new, expansive perspective. Scientific methodology itself would be refined. Researchers would need to design experiments with multiverse effects in mind. Statistical models, data analysis techniques, and error filtering methods would evolve to account for phenomena that were once dismissed as noise. Experiments in quantum labs, gravitational wave observatories, and cosmology satellites would be coordinated to detect cross-domain correlations, forming a unified approach to measuring influences that span universes. Long-term technological applications could emerge in areas we cannot yet fully predict. If quantum systems are influenced by other universes, it could open pathways to entirely new forms of computation, communication, or even sensing. Space exploration could incorporate data about multiversal effects to plan safer and more efficient trajectories. Biological studies might reveal previously hidden factors in evolution and consciousness, influenced subtly by interactions with parallel realities. Future experiments could target specific predictions of multiverse models. For example, high-precision quantum systems might test for branching interference patterns. Gravitational wave detectors could focus on anomalies in frequency or amplitude that do not match any known astrophysical source. Cosmological surveys could map CMB anomalies with finer resolution, looking for patterns consistent with bubble collisions or energy transfers from other universes. Each experiment would feed data into simulations, refining predictions and expanding our understanding of how multiple universes might interact. The integration of these fields represents a new era of science. Quantum mechanics, cosmology, and gravitational physics are no longer isolated disciplines. They converge in a coordinated effort to measure phenomena beyond our universe. Each anomalous signal, each subtle deviation, becomes part of a larger map of reality. This multi-scale investigation is unprecedented, turning what was once speculative into an empirical frontier. Even practical technologies could benefit indirectly. High-sensitivity detectors developed for multiverse research could improve medical imaging, environmental sensing, and communication systems. Quantum computing advancements driven by new understanding of decoherence and cross-universe interference could produce devices far beyond current capabilities. Space exploration and satellite systems could gain enhanced precision from models that account for subtle cosmic fluctuations. Visualizing the multiverse. Imagine the universe as a vast, stretching ocean. Every star, galaxy, and planet floats on the surface, but underneath, currents move in ways we cannot fully detect. Now imagine that this ocean is not alone, that other oceans exist, each with its own stars, its own galaxies, and its own physics. These other universes may ripple and shift alongside ours, sometimes interacting, sometimes isolated, but always expanding. Scientists attempt to map this invisible terrain through simulations and mathematical models. One method begins with cosmic inflation, the rapid expansion that occurred just after the Big Bang. Inflation theory predicts that different regions of space expanded at slightly different rates, creating bubbles of reality. In some simulations, these bubbles grow until they collide with one another. When two bubbles meet, they don't merge like soap bubbles. They interact violently, sending waves through the fabric of space-time. The collision leaves marks, energy fluctuations, gravitational disturbances, and subtle temperature changes that might still be detectable in our universe. One of the most famous of these marks is the cold spot in the cosmic microwave background. In simulations, a bubble universe hitting ours produces a region slightly colder than its surroundings, stretching across millions of light-years. Animated models show the moment of impact as a ripple spreading across the surface of our universe, distorting the cosmic radiation like a stone thrown into a pond. These simulations give researchers a sense of scale and direction, what to look for when scanning the sky for evidence of external influences. Quantum mechanics adds another layer to this picture. On a subatomic scale, particles don't behave like billiard balls. They exist in superpositions, multiple states at once until observed. In the many worlds interpretation, every possible outcome of a quantum event splits the universe into parallel branches. A single electron might go left in one branch and right in another, creating a cascade of realities where every possibility is realized. Animated representations of these branches show a tree that splits endlessly, each branch representing a universe slightly different from the last. These branching realities are not just theoretical. Experiments in entanglement and superposition hint that multiple branches could subtly influence each other. Simulations illustrate how tiny correlations between branches might appear in our universe as unexpected deviations in particle behavior or energy distribution. Each quantum decision multiplies the number of possible universes, creating a landscape of infinite possibilities, overlapping and intertwining in ways that challenge intuition. Colliding universes are a particularly dramatic scenario. In some models, a universe expanding faster than ours could intersect with our space-time, sending ripples of energy across vast distances. Simulations show these collisions producing elliptical or circular distortions in the cosmic microwave background, subtle gravitational waves, and bursts of energy that propagate in unexpected directions. The patterns are not random. They follow the physics of inflation and energy transfer, offering a roadmap for what to look for in real observational data. Particle physics adds even more detail. High-energy collisions in accelerators simulate the conditions of the early universe. When particles collide at extreme energies, they recreate environments where multiple quantum outcomes occur simultaneously. Animated models depict a flurry of branching paths, each representing a different version of reality, with particles splitting, recombining, and interfering with one another. These visualizations help researchers understand how multiverse interactions might leave fingerprints in energy distributions and decay probabilities measured in the lab. Some simulations focus on hidden dimensions predicted by string theory. In these models, each universe exists in its own set of dimensions, stacked like sheets in a folder. Occasionally, these sheets touch or overlap, creating local distortions that could produce measurable effects in our universe. Animated representations show these dimensions as layers, bending and twisting in response to forces beyond our perception. The intersections create subtle fluctuations in gravity, particle behavior, and even light propagation, offering another possible signature of multiverse interactions. Gravitational waves add movement to these scenarios. Imagine two universes colliding not in physical matter, but in the fabric of space-time itself. The collision generates waves that ripple across both universes, altering the distances between points in space in imperceptible ways. Simulations illustrate how these waves would appear to detectors like LIGO and Virgo. Faint oscillations superimposed on normal cosmic signals, stretching and compressing space-time, just enough to be measurable but not destructive. These models help researchers differentiate ordinary astrophysical events from potential multiverse interactions. Even subtle quantum experiments can be represented in these models. Superposition experiments show clouds of atoms splitting into different paths, with simulations mapping the probabilities of each outcome. Entangled systems are represented as connected nodes, with lines of influence stretching between particles. When additional hypothetical universes are included in the model, faint cross-connections appear, illustrating how multiverse effects could influence the behavior of matter in ways too small to detect directly, but still measurable with high-precision equipment. The simulations are not just academic exercises, they guide real-world observations. By modeling what a universe collision would look like in both the CMB and gravitational waves, researchers can focus telescopes, satellites, and detectors on regions where the effects are most likely to appear. Quantum simulations inform the design of particle accelerators and entanglement experiments, highlighting the parameters most sensitive to multiverse interactions. In this way, simulations bridge the gap between theory and experiment. Animated models also help communicate these complex concepts to broader audiences. While the physics involves equations and probabilities, simulations translate these abstract ideas into patterns, shapes, and interactions that can be interpreted intuitively. Cold spots, gravitational ripples, quantum branching, and dimensional overlaps can all be represented in ways that are visually coherent without oversimplifying the underlying science. This approach makes it easier to grasp the scale, frequency, and implications of multiverse phenomena. One of the most striking representations involves bubble universes interacting over billions of years. Animations show one bubble expanding faster than another, eventually intersecting and producing ripples in both structures. The energy exchange can be traced, showing where collisions produce high-energy spots, gravitational distortions, or potential influences on quantum systems within the affected universe. These models demonstrate that multiverse interactions are not catastrophic in most scenarios, but leave measurable fingerprints. Simulations also explore variations in physical constants. If gravity, the speed of light, or quantum rules differ slightly in neighboring universes, collisions or overlaps could produce observable anomalies. Animated models map these differences as color gradients, distortions, or waveforms, illustrating how even tiny variations could leave detectable effects in cosmic radiation, gravitational waves, or quantum experiments. These representations make it clear why multiverse theories predict patterns that appear across multiple observational domains. Quantum branching can be visualized as a network of pathways extending from every decision point in a particle system. Each path represents a possible outcome, and each intersection could subtly influence others. By simulating millions of these pathways, researchers can see where probabilities align with experimental anomalies, suggesting that what appears as noise in the lab may actually be a faint echo of neighboring realities. Collisions between universes are also represented in time-lapse sequences. A neighboring bubble expands and interacts with ours over millions of years, sending waves through space-time that gradually diminish in intensity but remain detectable in certain observables. These animations help illustrate how ancient events could leave traces visible today in the cosmic microwave background, gravitational wave signals, or subtle quantum effects in laboratory systems. By combining these different scales, cosmic, gravitational, and quantum, simulations create a unified representation of multiverse dynamics. Large-scale cosmic interactions influence mid-scale space-time ripples, which in turn might leave subtle signatures in microscopic systems. Each layer reinforces the others, showing how the multiverse could leave traces in multiple realms simultaneously. This approach also allows for scenario testing. Simulations can vary the size, energy, and frequency of bubble collisions, or adjust the strength of interactions between quantum branches. By comparing predicted patterns with actual observational data, researchers identify which scenarios are most plausible. These models help refine experiments, guiding telescopes, detectors, and particle systems toward the conditions most likely to reveal multiverse influences. Even in scenarios where universes do not collide directly, simulations explore how nearby bubbles could influence our universe through gravitational pull or energy leakage. Waves propagating through hidden dimensions, subtle fluctuations in quantum fields, or even the cumulative effect of countless parallel branches can all be mapped in these models. Animated sequences illustrate these effects as waves, shifts, or distortions spreading across multiple scales, showing that multiverse interactions are subtle but measurable.